Hi, Melissa. Is it okay if I test a screen share?
Yeah, sounds good, Kathryn. Let me stop there.
Do you see the presenter view or the main view?
The presenter view.
What about now?
That looks good.
Okay, cool.
It's great.
And the video is playing.
Yes. Are you good, Kathryn?
Yes, thanks.
Okay, sure, no problem. Thank you. Hi, Andrew.
Thanks.
No problem if you want to do a quick test.
Okay. Is my audio coming through?
Yes, we can hear you. Can you hear me?
Yeah.
Yes. Hi, John. I can hear you both.
And my screen. Oh.
How's it going, Andrew? Do you see the share screen button?
Sorry. So if I so is that being shown?
Almost.
Black.
It's black. Yeah. I see you have something full screen, but I don't see any text or anything. It's just black.
Oh, you don't see the actual presentation?
No.
Nope.
Okay.
I think when you share, it allows you to choose, which window.
Yeah.
you
I think
can-
that's my problem.
Yes, I think you either choose the PowerPoint. I always choose the PowerPoint if I'm doing a PowerPoint presentation. Then I choose the PowerPoint application.
Yeah, I'm trying to present off a web browser, so I think I'm gonna have to try
Oh, okay, then choose the web browser
different.
application.
Yeah, there we go. Um,
That's pretty good. Yeah. Let's see.
okay,
Yeah, that's very good. That's perfect.
they're
Yes.
working. Okay, great.
Full screen and everything.
Okay, great. And you get some puppies in the background too, which
Yeah.
hopefully won't be happening.
Okay, thank you. Yeah, luckily mine are being quiet right now. Does anyone else need to test out audio, any of the presenters?
Can you hear me?
Yes.
Okay, cool. I think that's fine. I don't think I need to test sharing. It should be okay. Thanks.
Okay. Sounds good. We're going to start recording then from Zoom.
Hi, everyone. I'm Jenny Smith. I'm going to be chairing this session, and I'm going to start just a hair early to be sure that our speakers get the full time allotted to them. Hopefully, everyone's feeling bright and energized on day 3. I know virtual conferences can be kind of hard, but hopefully at this point, we're all used to it. And so far, I think it's going really well, and everyone's learning a lot. So thank you all for being here. Our first talk today is from John Romein. John comes to us from the Netherlands Institute for Radio Astronomy. He's an expert in high performance computing, and he's going to be telling us about CPUs, GPUs, and FPGA imaging. Should be a really interesting talk. John, I'm planning to interrupt you. After 20 minutes, I'll just pop in and say it's been 20 minutes just to give you a heads up, or I'll do something different if you tell me to.
Yeah, well, no, that's perfectly fine. Can you see the slides?
Yeah, look great.
Okay. Yeah. Let me show our experiences with the OpenCL toolkit from Intel for FPGAs. Actually, this is the work from many people, both from Astron and from the Netherlands eScience Center. And well, frankly, this is not an outline, but my intention is just to take you through our endeavor to bring high-level programming to radio astronomical processing. And I will share my experiences, show the things that we learned, that I liked, that I did not like. And this all started, I guess, some 6 years ago or so, when Altera introduced an OpenCL compiler for FPGAs. And another new thing for FPGAs was that the ARIA 10s were the first FPGAs to have real floating point units. And the third new thing was that FPGAs were more and more tightly integrated with CPU cores. And these 3 developments had 2 consequences. One of them was that for the simple things that we already did on FPGAs, like filtering, beamforming, etc., it should be possible to program this with less effort than in a hardware description language like VHDL or Verilog. And the second consequence was that we would be able to implement much more complex HPC applications than was humanly possible before. So we started exploring these technologies for signal processing and for imaging purposes. First, very brief introduction to OpenCL. It is a common language for any kind of accelerator, GPUs, FPGA, Xeon Phi, DSPs, whatever. And well, there's a lot of similarity with CUDA. Essentially, it's C plus some extensions to express parallelism, to do software-controlled caching, but it's clearly tailored towards GPUs. And the idea is that with your application, that the real compute-intensive part is then written in an OpenCL kernel and offloaded to the GPU or FPGA, where that kernel will execute your code. And this is an example that computes and prints a Fibonacci number. And this actually works on an FPGA. This way you can do a printf from an FPGA and get the text on your screen. So the OpenCL compiler generates a data flow pipeline from your code. For example, these 4 commands, these perform a complex multiplication. And on the right, you see the data flow pipeline that is generated from this code. And the idea is then that every cycle, new data goes into this pipeline, and with a few cycles delay, a new result is produced also every cycle. So with the OpenCL approach, you get a very nicely structured, layered approach where on top in green, there's application code where you program your algorithms, you declare your data structures. It's very high level. That you have to do yourself. But in the middle, you see the compiler generated stuff. That is all things that you get for free from the compiler, and that is mathematical operations, address calculations, memory accesses, register allocations, the use of FIFOs, which is called channels in OpenCL, and you get that for free. And at the bottom, there's an OpenCL board support package that provides the low-level access to the hardware components on the board. And that is actually the only thing that you still need to program in a hardware description language. So if you compare OpenCL for FPGAs to OpenCL for GPUs, we see that it's really very different, and that is due to the architectural differences between FPGA and the GPU. The FPGA is really a data flow engine, and then GPU is a processor that executes instructions, and that is very well reflected in the way you program either accelerator. So in practice, there will be hardly any code reuse between an FPGA and GPU. Also, it turned out to be necessary to extend OpenCL with several extensions to make it easier to program FPGAs. For example, the compiler supports channels. These are FIFOs, which you can use to stream data from one OpenCL kernel to another. Also, there are different methods to express parallelism for GPU applications and for FPGA applications. The unroll example means on an FPGA very different thing than on a GPU. On the GPU, it just creates 4 times larger code, while on the FPGA this means do 4 loop iterations concurrently, so that introduces parallelism, while it does not on the GPU. And also with GPUs, you use the hardware that is there, while on FPGAs, you create the hardware. So memory bank, for example, the GPU has a fixed size memory bank. While on the FPGA, you can create whatever you like. And usually the compiler can create the most appropriate memory bank for your specific memory instance. And there are many, many more differences between programming for GPUs or for FPGAs. But if you start programming, the first thing you do after having written some code is run it in an emulator, so that you can quickly see if your code works, is functionally correct, and does not contain bugs. But it does not give you cycle time accuracy. It's only to verify the correctness of your program. And then the next step is to see the compiler feedback. After a couple of minutes, the compiler generates an HTML report, which gives very much information about the resource usage, for example. It gives you warnings about where the pipelines could stall. On the right, for example, it shows how it created a memory bank, or 2 banks actually, and access to this memory bank, and it shows that it inserted 2 arbiters, and that's probably not what you want. So this feedback is really indispensable, because this way you can verify whether the compiler really generated the thing that you had in mind. And then after you're really happy with the HTML reports, you compile it for real, wait for hours, and run it on the real FPGAs. And then you can use a profiler if you want to do so. So we tried this on several applications. I will discuss 2 of them. One of them is an imager. Let's discuss this first. The imaging application, it's from the image domain gridding imager, which is really a complex application. And as a result, the data flow pipeline, it's one very large data flow pipeline that fills the entire FPGA. That's also a very complex data flow pipeline. And what is different with GPUs is that with FPGAs, you really have to think about how you divide all your resources over these sub-pipeline components, so that all these sub-pipelines, the data flows through it fast enough. If some sub-pipeline is too slow, then your whole pipeline will stall. But if a sub-pipeline is too fast, you probably use too many resources for it. And then, yeah, you could have used these resources for other things. And eventually, we had highly optimized imaging implementations for CPU, for GPU, and for FPGA. And we compared this, and we compared how this worked on the different architectures. We compared programming models, the optimizations that were necessary for them. We compared performance and energy efficiency and programming effort. And this is, by the way, this is all in a paper. If we look at the performance on the left and the energy efficiency on the right, we took a CPU, GPU, and an FPGA with a very similar peak performance. But on the left, you see that the CPU was really unable to get even close to that peak performance. The performance on the FPGA was already much better, but on the GPU, it was still even better than that. And on the right, the energy efficiency, you also see that both the GPU and FPGA were much more energy efficient than the CPU. But the GPU was even more energy efficient than the FPGA. There were many other things that we learned. Probably the most important thing is, the architectural difference that for the FPGA, you have to create a data flow engine, and you really have to rethink your algorithm so that it fits a data flow engine. So eventually you will not be able to reuse any code. And you have to think about the way you use resources. You have to think about timings, the occupancy, so that all multipliers are used every cycle. But if you look at it from a distance, these optimizations are fairly similar. You have to, for each of these architectures, you have to exploit parallelism to get maximum performance, you have to optimize memory performance by hiding latencies for these memories. You have to make sure that you coalesce data to maximize memory bandwidth. And most importantly, you have to cache data at various levels to reduce memory traffic at all. But so at a high level, these optimizations are similar, but the way you implement and achieve these optimizations are very different for these architectures. And on top of that, there are, of course, some architecture-specific optimizations. Eventually, we think that indeed this toolkit is much easier to use than a hardware description language, and that it makes FPGAs accessible to a much wider audience. Still, there's a long learning curve. It will really take months before you will really get used to this toolkit and learn how the compiler works and what it understands and what it does not understand. Still, it's not as easy as programming GPUs, and that is mostly because you have to distribute all your FPGA resources in this complex data flow pipeline. And what we also found that it is difficult to optimize for a high clock frequency. You do get good feedback on resource usage so that you can optimize for a low resource usage, but optimizing for frequency is much more difficult because the feedback that you get from the toolkit is not that useful. And in general, yeah, we see that over the years that these tools are still maturing. Especially at first, we run into quite a number of compiler bugs, but Intel fixes them. And over the years, they really have improved. So, yeah, we've first been working with this ARIA 10 board, which came with an OpenCL board support package, but the board support package did not support the 40 gig network interfaces that were on this board, and that was a pity. So, well, this was the work from Reinier from Bela. He added 40 gig Ethernet support to this board support package so that we were able to send and receive Ethernet packets from an OpenCL program. And that was really cool, I thought. So we started even thinking further. We also have this UniBoard Squared that you may have seen before. It contains 4 ARIA 10 FPGAs, and we will use it for the LoFar station upgrade. And we were wondering, would we be able to program UniBoard Squared in OpenCL? And the straightforward answer would be no, because OpenCL needs a host CPU. The host CPU invokes OpenCL kernels, and the host CPU manages the off-chip memory. So it has an important role. And the problem is that the FPGAs on UniBoard Squared have no host CPU. There are no ARM cores or Xeon cores nearby. But with some hacking, we somehow made it half work. And that is by using kernels that start immediately running after the board is powered on. These are called auto-run kernels. But we cannot use the off-chip memory. And that is, yeah, that is because of interaction with the CPU that is not there. So we never managed to to enable the DDR4 memory on the board, but all the other hardware components on the board are now controlled by a board support package. And even though we could not use the memory, we still could do a first a nice demo where we attached a loafer antenna to an analog to digital converter. And in green, we wrote an OpenCL program that received the samples from this ADC, did some filtering on it, and packetized the data and sent it over the 40 gig Ethernet links to a regular machine. And this all was implemented in, well, I think in 2 months' time or so. Most of the work was in the board support package. So we started thinking even further. Could we use it for the Loafer 2 station firmware upgrade? We already started programming the firmware for the Loafer 2 upgrade in VHDL, but we were wondering, could we then do part of the functionality in OpenCL? And we tried this for 3 or 4 months or so, but eventually we stopped this. And the most important reasons for that was that while there was no CPU available on UniBoard Squared, it also made debugging very difficult. So it did not save us time anymore. And the other reason that the firmware design was really not made with OpenCL in mind. So, for example, it was expected to run at a fixed clock of 200 megahertz, while the OpenCL environment does not run at a fixed frequency, but at a compiler-generated frequency.
Hi, John. Just letting you know it's been 20 minutes.
Well, I'm almost ready.
Nice.
Yeah. So, well, we are currently working on an OpenCL FFT generator so that we do not have to write FFTs by hand anymore. This is work that we're doing with the Netherlands eScience Center. And another demo that we are preparing is that we want to stream data from an FPGA to a CPU-GPU machine using RDMA, so that the overhead on the CPU is lowered compared to sending data with plain UDP packets. And the FPGA, of course, is then programmed in OpenCL. So yeah, wrapping up. Generally, I think the whole environment is a great improvement over a hardware description language. Well, what made it very different from GPU programming is just the different architecture, the fact that you create a data flow pipeline. So therefore we saw that there was no portability with any GPU code. Having said that, if you look at the table, the GPU outperforms the FPGA really in all aspects. So if you have to use an FPGA because you have to interface to an ADC, for example, or do really real-time packet processing, then I would go for this environment. But if you do not have to use the FPGA, I would prefer the GPU. And a few words of thanks to our funding agency. And with that, I think there's time left for some questions.
Great. Yeah, thanks so much. I can read out some questions from the chat. I think we probably have time for most of them. So the first one is about the A10GX card. The question is, which runtime version did you use? How long was the algorithm running, and did you observe any memory leaks?
This card?
I think so. A tool can, it's a tool's question, a tool can jump in if that's not right.
Yeah, I think GX is there in the table just before the slides.
Yeah, I cannot see the chat. So
I think it's just a few slides earlier, John,
just a few slides earlier.
where you had a table. Are we getting warm at all?
Yeah, it's earlier.
So can you say stop?
Stop. Yeah.
This one?
The comparison of GPU and a CPU.
The comparison in GPU and CPU. Here.
Yeah.
Yeah.
Yeah, I
Okay.
mean, you can choose any card. Just I wanted to hear about memory leak. Have you observed, or which runtime environment did you use?
The runtime. This was done on the same Nalotech board on the FPGA. Which runtime?
Okay,
did we
must be
use?
17 then. 17 or 18 should be, right?
Yeah, yeah. No, I'm not sure if this was still done on the 17 because Reinier van der Wallen upgraded it to 19. So he modified the BSP for the newer compilers.
How long your algorithm was running? Did you observe any memory leak, or it was breaking in between, kind of?
I did not observe any memory errors or whatever, but I did not try to run them for 8 hours.
Okay, maybe it's because of that. Thank you.
Another question I'll ask is, has to do with timing optimization. So is there a way to optimize timing with OpenCL? Can you add register stages, for example, which could be used for retiming or moving logic over register stages?
Yes, there's an intrinsic that does so, but you really have to be very well aware of what you are doing, or what the compiler is doing to use them. But there you can indeed generate extra timing stages.
And then I think, lastly, a couple of people are curious if you looked into more sort of like hand sculpted Verilog, HDL, or HLS implementations on an FPGA and seeing if the performance was better from those programming techniques.
I did never implement, especially not the de-imaging application in HDL, because it's way too complex to implement this in an HDL. In fact, I did not implement anything in HDL because I refused to learn an HDL because I think it's too low level. But generally, I think that you can create design that runs at a decent clock frequency, and it does not necessarily take more resources than an HDL design would take. Of course, you will be able to reach 10% better performance by optimizing everything by hand in an HDL language. But generally, I think the OpenCL environment does a good job. Does that answer the question?
Yeah, I think that's great. Okay, looks like I think maybe we have, well, yeah, okay. I will defer the rest of the questions to the chat. Whenever you stop screen sharing, you should be able to see it again. And I'll introduce the next speaker. So the next speaker is Talon Myburgh. Talon is also affiliated with Casper. I guess Talon didn't want me to say any affiliations, but they'll be talking about introducing DSP cores and research conducted in integration and documentation and understanding how to verify Casper HDL blocks, something that we're all really interested in. So Talon, you've got 2 minutes until it's 8 a.m. proper. So you can definitely pause if you'd like, or feel free to get started.
Okay, So hopefully you can all hear me and I'm not still muted. Pretty tough act to follow because I'm here to tell you that you should work in HDL development, and hopefully I can explain to you why. So over the past year, I've had the opportunity to explore the development of Casper's DSP in HDL. In this presentation, I hope to show you the reasons behind this decision and why it is a compelling choice for Casper DSP development. Now, to speak of DSP in radio astronomy mostly implies that you're speaking of an FFT or PFB. I explored many options for open source PFB designs, including starting a C-based design for HLS, but was mostly discouraged due to lack of features and inefficiency. Fortunately, Astron open sourced their VHDL wideband PFB on open cores and gave this project its footing. While the HDL was largely RTL based, it had been designed to work on Intel FPGA hardware. As such, it required adjustments for it to work on Xilinx hardware whilst retaining Intel functionality. I had to add the option to build with Xilinx IP and remove the Intel memory map functionality to reintroduce later with Xilinx alternatives like Axie or Wishbone. Then, to make it more familiar to the Casper user, I had to expose interfaces, add useful functionality like shift registers and overflow registers, and thereafter, I focused on optimizations by way of additional RTL modules, directives, and optional IP generics in the HDL code. As HDL, we were able to fully compile the FFTs and FIRs in both Vivado and Quartus, and inherently, we had introduced a feature not present in the Casper DSP Toolflow before. We had started becoming FPGA vendor agnostic. But that was the easy part. This work, at its current stage, would not have been useful to anyone in Casper if it were not integrated into Simulink. After months of reading the only issued documentation for this approach and posting questions on every suitable forum to a largely mute audience, I integrated the wideband FFT, pipelined FFT, and polyphase filter bank into Simulink, and thereby into Casper's Toolflow. Presently, both FFT blocks simulate and look promising. Though they have been tested for most of their functionality, we do anticipate further issues, especially when members try to build for Intel with DSP Builder, which is untested. We have also had successful compilation for the snapboard, though we've not had the opportunity yet to put it on physical hardware. As it stands, we find that the Casper wideband FFT uses 25% less DSP and 50% less BRAM than the Astron one. The DSP discrepancy is in line with the expected gain from Casper having a biplex FFT and Astron not, while the BRAM discrepancy mostly arises from it not having an in-place reorder, like the Casper FFT does. Hopefully, with Casper adoption of this core, the Astron FFT will become as efficient, if not more. The FIR block must still be tested to simulate and compile, and thereafter we'll knit them together for a full wideband FFT. Unexpectedly, we introduced a second feature to the Casper Toolflow. Simulink blocks are thin, fast to redraw, and thereafter compile. And here you see me altering the parameters of an FFT and having it redraw. And mind you, this is over a remote connection to a server 16,000 kilometers away from me. And I know it's HDL development, and as John has expressed, it's tedious and difficult to work with. But with it, we do have faster compilation and simulation times, homogeneity across FPGA families, we can be vendor agnostic, and we gain low-level control. However, if you've ever developed an HDL, you know that while you have brilliant code that is explicit and specific, it is usually accompanied by proprietary bloated simulation software, documentation that is separately maintained and generated, and high-level core wrapping that is manually implemented and usually proprietary. What we'd instead like to have is a collaboration on our HDL code that is continuously and automatically tested and documented. Furthermore, we'd like that the HDL extend all the way to the top level where block level designs and simulation are still in HDL. this brings us to our ideal development cycle, where we simulate, design, inspect, and verify, collaborate, host, develop and document, access, and deploy. The hope is that all of the energy in this cycle is put towards the development of HDL, and not the maintenance of tests and documentation, nor the development of wrappers and simulation environments. Finally, we'd hope that all of this remained open source software. Access and documentation would be provided by hosting the HDL on GitHub, which it currently already is. And we'd have automated documentation triggered by GitHub actions and likely hosted on Read the Docs. And below there, I have an image of the current Read the Docs documentation for the core that is on GitHub that I have. And then collaboration would be empowered by continuous integration suites of automated actions that test and verify the IP by way of an open source simulation tool like GHDL. And I've demonstrated this before to a select group of Casperites, where we make use of VUnit and Jenkins to continuously verify the pipelined FFT core. The current Casper flow encourages block level design that instantiates block level entities which generate or wrap hidden HDL. And this is a top-down approach. Perhaps better would be to flip this around and go from verified HDL to lightweight generated block entities, to lightweight block level design, and all of this in an HDL-centric flow. Existing tools and platforms could provide this framework for such a flow. And with the correct choices, it would be open source. And we still have investigation to do into some of these tools, but it looks promising, and hopefully some of the new radio guys at this conference can guide this. So with such an HDL-centric development cycle, we'd benefit greatly from tooling that provides contemporary software development features like linting or relational hierarchies that describe the instantiation of modules from a top-down perspective, like this, generated by Doxygen. We'd also require signal drivers in our design environment and real-time RTL parameter resolution for simplified debugging. And I feel that with these contemporary software tools made available to the Casper developer, RTL development would be greatly simplified and made far easier. But as I said, it all starts with HDL BSP. So do you have any questions?
Thank you. Perfect timing. I didn't have to give the warning. So one question was, where was that server that's 16,000 kilometers away?
That's at Berkeley University. I'm currently in South Africa, so I work on a server at Berkeley University.
Nice. I have a question. So you mentioned that wideband FFT that you ported into Simulink. Can you talk a little bit about some of the options? Like, what's the maximum size you could make it, for example? Is it only powers of 2? Are there any other interesting features that you can customize with that block that the normal standard Casper FFTs don't have?
So the current size, well, it's technically unlimited, but a little bit of work has to be done to extend the FFT past 8K in points. The wideband factor being how many pipelined FFTs, or rather how many simultaneous samples it accepts per time, is fully customizable. It makes use of some functionality that the Casper FFT doesn't have, like an overflow register that I implemented that explicitly states at which stage overflow occurred. And that's obviously combined with the shift register, which governs shifting at every stage. But mostly we've tried to go for a design that as an interface looks very familiar to Casper users. It also does a complex FFT or the processing of 2 real FFTs with a separate function on the output. Outside of that, bitwidths are generic. Control over whether to instantiate DSP or BRAMs is generic, etc. Yeah.
Great. We have a follow-up question. Did you implement any of your FFT dynamic shift schemes?
No, I did not. This currently still uses the static shift scheme, although it can be configured at runtime because it's just a simple port in the VHDL entity. But no, there's no like look-ahead approaches or anything like that for the shift scheme. Anything else?
I'll give people one more moment to post questions in the chat.
Yes, to answer Andrew. Oh, yeah, a whole bunch of questions have arrived, but I believe simulation in Simulink, yes, you can do so. Shall I proceed with the questions or?
Yeah, keep going.
Okay, we bring up the chat.
We have another.
Yeah, we can simulate in Simulink. Qualitative or bit level accurate. At this stage, we have test benches to evaluate whether it is bit level accurate. It's not formally verified in that we have massive coverage maps that we run over. It's very much suited to specific inputs, to specific outputs, and that's tested. But it is on a bit level. It is on a bit level. The features that the Astron FFT has that aren't in the Simulink book that might be useful. Geez, possibly, but if you ask me this during a presentation, I'm likely to forget, which seems to be the case. There were, I mean, the Astron FFT can build for Intel or Xilinx, but that's already in the Simulink block. So no, I think I've pretty much extracted everything from the HDL and made it available in the Simulink block. I'll see there's another message. Display talk. Thank you.
Awesome. Well, if no one objects, I suppose we can just move on a couple minutes ahead of schedule. The next speaker is Morag Brown. Morag Brown's coming us from South Africa Radio Astronomy Observatory, and they'll be telling us about a comparison of different FFTs. This will be a nice flow from the last talk. Looks good.
Thanks. Sorry, I couldn't find my unmute button. Anywho, hi everyone. I'm Morag. I'm a postgrad student at the University of Cape Town, and I currently work at Chirindo. Apologies for not having my video on. My internet's struggling a bit tonight. Anyway, welcome to FFT Mania. Before I get started, I'm just going to give an overview of what's in this presentation. I'll obviously tell you what my research project actually is. I'll then talk briefly about the FFTs that are involved, my plan for testing said FFTs and what my testing setup looks like. I'll then go through some preliminary test results and finally talk about what I plan to still do. So my project involves the comparison of different FFTs for FPGA hardware. There are quite a few different FFTs out there. I found some literature on optimized versions of the Xilinx FFT and Ryan Monroe's optimized Casper FFT, but most in-depth analysis focuses on resource usage and speed and not much else. If you were at the previous talk, which I assume you were, you'd know that Talon has brought the Astron wideband HDL FFT into the Toolflow, and I thought it'd be nice to get an idea of its performance against the others. So the FFTs being tested are the Casper and Astron wideband FFTs and the Xilinx SSR FFT. I'm testing in both simulation and on hardware, but I'll get into more detail on that in a few slides. First, I'm just going to quickly run through the FFTs being tested. The first is probably one that most people are familiar with, the Casper wideband. So real to complex FFT that uses Hermitian symmetry to calculate a real FFT for half the resources per FFT core. So for a Dmux factor of L, this core computes L over 2 many endpoint FFTs for log 2 M stages, followed by M over 2 many L point FFTs for log 2 L stages, for a total of N over 2 log 2 N computations per endpoint FFT, as opposed to the N log 2 N computational cost of a standard FFT. And next is the Astron wideband. It's able to compute both complex to complex and real to complex FFTs. It also uses the Hermitian symmetry trick, but this one instead calculates the FFTs of 2 real inputs for half the resources. And the architecture is similar to that of the Casper wideband, and to stick with what's in the diagram. For a Dmux factor of P, there are P many M point FFTs followed by M many P point FFTs to tie everything together. And this still results in N log 2 N total computations, but a single core can be used to calculate the FFTs of 2 real signals. So you can input one signal into the real and another into the imaginary input of the core, and it calculates both still for only N log 2 N computations. So effectively half the resources per FFT. And I should say here that I still need to figure out the output of this FFT, so any test results on this core are still to come. Here we have the Xilinx SSR FFT, where SSR is the super sample rate. As with the Casper and Astron widebands, it processes multiple samples per clock cycle, where the number of samples processed is determined by the SSR factor. And this is just a screenshot of underneath the mask here, this vector to scalar block demuxes the vector inputs, concatenates them into one long thing, and sends them off into the FFT. I don't really know what happens in this black box other than general FFT shenanigans, but as with anything that involves the FFT, I assume it's magic. The last FFT is the fastest Fourier transform in the West, which is a C library, and this is the FFT against which I'm comparing the other FFTs. It's also capable of calculating complex to complex and real to complex FFTs. And the version I'm using is double precision, but single and double long are also available. This is just an example of some code on using the library. This argument FFTW measure tells the FFTW to take a few seconds to find the best way to compute the transform and sets up an optimized plan. But another argument, FFTW estimate, can also be used. And if it is, then the FFTW sets up a plan that seems reasonable, but probably isn't optimal. And then there isn't a convenient block of the FFTW to use, so I just have a picture of Clint Eastwood, but I don't have any ideas as to what his FFT calculating abilities are, sorry. And jumping into the actual testing now, at the highest level, this is what my simulation setup looks like. I have a bunch of files that contain the values of my generated inputs. These are read and input into my various Simulink designs containing all the configurations of the 3 FFTs being tested, as well as into my application that performs the FFTW. And then I have a Python script that runs the FFTW application, loads the output, calls the corresponding outputs for each of the simulated FFTs, does some numerical analysis, and plots various things. And then the input signals I'm using are both full scale and scaled by 1 over the length of the FFT. And then the signals that I'm using are an impulse, a real sinusoid plus noise with a signal to noise ratio of 30 dB, and then only noise, and my noise is modeled as a white Gaussian distribution. I also want to test a signal with 2 harmonics close together to test how each FFT resolves the different frequency components. And the sampling frequency of these signals is 1.712 gigahertz, because that's what the MeerKAT digitizers sample at. And I'm testing a couple of different signal frequencies depending on the bandwidth. I have signals that are centered in a frequency bin and signals that aren't, so I can test spectral leakage across the FFTs. The FFTs themselves are 1K, 4K, and 32K point FFTs. These are just the different configurations for our F engine. As I said earlier, the FFTW is double precision floating point, and then the simulated FPGA FFTs all take an input with a bit width of 18 with a binary point at 17, because this is typically what's used on the FFT input in a PFB. And in terms of shifting, where shifting is a division of 2 at specific butterfly stages to avoid overflow, I'm shifting aggressively, so at every stage, then every alternate stage, and then no shifting at all. And I'm also testing for different amounts of parallel demuxed inputs for the sake of completeness. And then the main thing I'm testing for in simulation is the effects of quantization. The simplest comparison I'm doing is finding the quantization noise. And to do that, I'm just subtracting the simulation outputs from the FFTW output and averaging the result, which gives an idea of the accuracy of the tested FFTs. For the more statistically inclined, I'm also using correlation to calculate a sort of quantization efficiency. And to do this, I'm just calculating the Pearson correlation coefficient of each simulated FFT output with the FFTW output. And then I'm also measuring the time it takes to simulate the FFTs, because the Casper FFT in particular can take forever to simulate. So I want an idea of how the other two compare in performance. And it wouldn't be a good academic project without at least some plots. So I have a couple of those too. And finally, I'll be testing on hardware. The current idea is to use the DSIM that our CBF team uses. This simulates the output of our digitizer and can output a pure tone as well as a tone with noise. This is sent over 40 gig Ethernet in the form of speed packets and will be sent to an awaiting scarab on which my FFTs will be tested. The scarab will unpack the data, perform the FFT, packetize the data, and send it out over 40 gig again, where a capture script will capture and process the output, on which I can perform further analysis. So now for some simulation results. I present these with the extreme caveat that they are very preliminary and also very incomplete. As I said before, I haven't managed to decode the Astron FFT output yet. So the only results I have to offer for this are simulation times. These are also only results of a 1K FFT with a Dmax factor of 8. I haven't tested any other configurations fully yet. So in the case of the Casper and Xilinx FFTs, I've gone with a simulation length of twice the FFT length, and Casper takes an average just over 70 seconds to simulate, while Xilinx takes just under 40. And the number of cycles before the first valid output data for Casper is 704, while for Xilinx this is 431. The Astron FFT has a latency greater than double the FFT length, so to get some quick results, I went for a simulation length of 4,000. And even so, it proves to be the fastest in terms of simulation time, but there is a greater delay before the first valid outputs. In terms of testing different signals, I've tested a signal at 167 megahertz, which is centered within a frequency bin, and a signal at 250 megahertz, which is not. In this case, I've just used a pure sinusoid with no noise as a baseline metric. And if we look at this plot with the output of the 167 megahertz signal, we see a fairly narrow spike. And if we look at the output for the 250 megahertz signal, we have a wider band as the spectral content has been distributed more across neighboring bins. And of course, this is to be expected, as is the quantization noise we see here, but it's nice to have confirmation that things are working as they should, if nothing else. And then taking a look at some actual numbers more or less confirms that the spectral leakage across the two signals, the two FFTs, is similar. The correlation between the simulation outputs and the FFTW outputs is quite high for both signals, and they both have similar correlation coefficients. And in terms of shifting, I've shifted at every stage and alternate stages. I apologize for not having results for no shifting, but I was having overflow issues, and that's not currently the focus of these results. So shifting at every stage seems to yield less quantization noise than at every alternate stage, but shifting at every stage results in a less accurate signal if we go by correlation. And I think this makes sense considering you're dropping more information and therefore losing more precision. I've also done the same results matrix for a sinusoid with noise. Nothing truly groundbreaking here. Same sort of trend for a lower quantization noise, for more shifting, with a lower quantization noise, sorry, but a lower correlation between the fixed point FFTs and floating points. I'm not willing to draw any conclusions about the accuracy performance between Casper and Xilinx as yet. I haven't run anywhere near enough tests for that, but they do at least seem to be competitive at first glance. And then in terms of hardware test results, I have no test results here as of yet. I will be testing for functional verification, resource utilization, speed, and build times, and hopefully everything will work as expected, but we'll see how it goes. And yeah, finally, just on the list of things that I need to do, need to figure out the output of the Astron FFT, run simulations for all configurations for all FFTs, do a functional hardware test of the Astron FFT just to make sure that it at least runs on hardware as we expect it to, and then thorough testing on hardware for all FFTs and their configurations. And that's all I have for you today. Thank you.
Thanks, Morag. That was awesome. I'm so happy you're doing this. I think this will be this already is and will continue to be super valuable for everyone in the community. Decoding all the FFT madness. Okay, you've got a couple questions. So the first one, the Xilinx SSR FFT, there's been concerns expressed, and Arash is bringing this up, that there's no reset signal on that FFT. There's just basically a T-valid that goes in, and if your T-valid drops low, you could lose count of which bin is coming out. And he was asking if you put in any extra logic or anything to deal with framing synchronization. I don't think you would have to unless you were explicitly testing that. But if so.
No, I haven't. I've basically just been going the easiest route and hoping that nothing weird happens in the interim.
Nice. I'm using that block too, and that's basically what we did as well. Okay. Oh, sorry, the chat is moving. Okay. So the other question is trying to get at those differences in the noise between the Casper and Xilinx FFTs. So you might want to go back to that slide with the noise correlation. Asking if they're using, basically trying to figure out if you have any ideas for where the difference is coming from. So the suggestion was maybe the bit width for the twiddle factors is different, but I don't think you have access to the twiddle factors in the SSR FFT. I think it's totally black box.
It could be a difference in the twiddle factors. I know I have access to that. Sorry, I'm just trying to find the slide. There we go. I have access to that for Astron, and I think Casper as well, but Xilinx not. It's pretty much just a black box underneath there, so I have to use what they've given me, I guess. Yeah, so I think it probably could be the twiddle factors, but I guess we'll never know for sure.
Got it. Another question is if you have any information about potential maximum clock rate that these blocks could operate at.
That would be hardware dependent, I figure. Limited by hardware. I'm testing on a Scarab, so I'm definitely going to be limited by what the Scarab can handle. But otherwise, it really is dependent on the hardware that you're using, as far as I'm aware, in any case.
Right. And then James has a suggestion. I'll just read it out loud. It may be worth thinking carefully about hardware utilization / build times. A small design with an FFT by itself will result in a mostly empty FPGA. You might get more bang for your buck if you test in a very full design, such as a Scarab F engine.
Yeah, that is actually something I plan to do if I have time to just set these things to build, because that will take forever. But my current plan is to just kind of drop the FFTs in and out of the F engine design, if I have the time to do so, for the larger FFTs at least.
Awesome. Well, I'll end it there. Thanks so much for your talk.
Cool, thanks.
So next we have Brent Graner. Brent's coming to us as a postdoc at the University of Washington. Beautiful Seattle, that is my hometown. And they will be telling us about a new experiment whose acronym I've been trying to figure out how to pronounce.
Oh, we usually pronounce it CRESS. Like,
CRESS, okay. It's got the HE6 though.
Oh yeah, helium-6 CRESS.
Helium-6 CRESS, okay, awesome. Can't wait to hear about it.
Okay.
Go ahead.
Hopefully that means that everyone can hear me. Gotta get out full screen and unmute and video on and do the screen share. Sorry, just a second. And then do the presentation here. Okay, so hopefully everybody can hear and see everything I've got going on here. Yeah, thanks so much, Jenny, for that introduction. My name is Brent Graner. Thanks everybody for having me at the Casper conference. I have to admit right off the bat that I am not an astronomer or a digital signal processing or FPGA expert by any stretch of the imagination. So it's been very great and informative to be here with all of you. I'm especially grateful for everyone for recording their talks so that I can go back and watch them half a dozen times and get some understanding of all the terms and the jargon that I don't normally use. But I wanted to come here today to tell you all a little bit about the cyclotron radiation emission spectroscopy, or CRESS experiment, that we're putting together at the University of Washington here in sunny Seattle for purposes of looking for new physics in the context of helium-6 beta decay. But before I get into talking about the experiment, I want to contextualize the talk a little bit. I'll avoid going into much of the theory behind the work that we're doing, except to say that we're looking for evidence of physics beyond the standard model in the energy spectrum of nuclear beta decays. And I don't want to get too deep into the motivation behind looking for new physics in beta decay, except to point out that I have the great privilege of working with quite a few people at SEMPA here who are deeply involved in the Fermilab U1G-2 experiments that you may have heard about recently. So we think that, you know, there's blood in the water when it comes to looking for beyond the standard model physics, and we think that we have good cause to look for new physics by trying to measure small deviations from standard model predictions in the context of weak sector physics. I also want to point out that all of the pioneering work in this cyclotron radiation emission spectroscopy technique was also done by our collaborators in the Project 8 experiment, which is also based at the University of Washington. And also I have to admit, I guess they did all that pioneering work in the context of looking for trying to set neutrino mass measurements or limits on neutrino masses via the endpoint of tritium beta decay. Finally, I have to point out that nothing about our data acquisition and first stage analysis system is particularly impressive to people who are experts in digital signal processing or FPGAs generally. So this talk is really more by way of appreciation and to give you all a sense of the scope of the projects that we're trying to build with the Casper tool sets outside of the realm of astronomy per se. Okay, so as an experimentalist, I don't want to go too deep into the theory, as I said, but I will say that on a fundamental level, what we're looking for is hypothetical scalar and tensor couplings that exist outside the predictions of the standard model in the weak sector. The helium-6 beta decay is primarily sensitive to these hypothetical tensor couplings, and those tensor couplings are parameterized by this dimensionless Fiertz interference coefficient that we rather dryly term little b. And this little b is predicted in the standard model to have a value of 0. Of course, this being a question of fundamental symmetries, the people at the LHC are working along similar lines. And we believe that we can be competitive with them if we can measure this little b parameter to an uncertainty of about 10 to the minus 3 or better. Ultimately, we hope to push the technique to a limit of fundamental limit of 10 to the minus 4 or so. So earlier, I mentioned that we want to measure beta decay energies. And at this point, you may be asking what this has to do with this funny little b parameter. This is a plot of the very familiar standard model prediction for the energy spectrum of recoil electrons in beta decay, specifically for helium-6. And you may notice that you know, these electrons are fully relativistic. They're fairly high energy, get up to about 3.5 MeV. And this Lorentz factor gets up to a factor of about 8. And it turns out that that is advantageous for our purposes because what makes that high endpoint energy makes helium-6 a fairly good isotope for our measurement, because any non-standard model value for this little b parameter will give the whole spectrum this characteristic distortion that goes as the electron mass over its kinetic energy. And so we choose an isotope that has a high endpoint for its beta decay to give us kind of a long lever arm. So that factor varies substantially across the spectrum if in fact there is a non-standard model value for little b. And if that value is positive, we'll see a surplus of events at low energies and a deficit of events at high energies here. Okay, so that's the sort of the quick and dirty explanation of what we want to measure. This is kind of the cartoon version of how we want to go about measuring a beta spectrum. If we can detect the radiation given off by an individual electron that's orbiting in a strong magnetic field, we can run that signal into our data acquisition apparatus. In our case, that means a Roach2. And we can make a series of broadband FFTs. And from there, it's just a matter of stacking those FFTs up, identifying the peak power in each bin, and then seeing the electron radiate away a little bit of energy with time. And then every so often, if you have your source in the gas phase, that electron will smack into a residual gas molecule, lose a fair amount of energy quite abruptly, and then jump to radiating at a higher frequency. So that's what explains these kind of characteristic jumps. So this approach is really advantageous from the point of view of precision measurements because, except for these occasional gas collisions, our detection strategy avoids a lot of really, really messy energy loss mechanisms we don't want to have to go through and model all of the possible ways that an electron can rattle around in a plastic scintillator and deposit its energy in order to get a full accounting of how much energy any individual particle is depositing in our detector. And that kind of this massless detection strategy is a real big advantage over the kind of traditional ways that beta spectroscopy has been done in the past. And of course, making our measurement based on a frequency standard puts Professor Sharlow on our side as well. So that's where it's always advantageous in terms of making a precision measurement. So that's kind of the conceptual version of what we want to measure and how we want to go about measuring it. This is kind of the cartoon version of our experiment. And I wanted to show you this just to talk a little bit about how we designed this experiment, specifically why we want to use 2 sets of amplifiers here at liquid helium temperature. So when an electron comes off of a helium-6 atom that's been piped into this decay region, which is a cylindrical piece of waveguide here, it'll emit microwave radiation at the cyclotron frequency in both directions. And obviously, because we're working with fairly low power sources on the order of 10 to the minus 15 watts or so, we want to collect all of the power that we can. And sort of the quick and dirty way to do that would be to put an RF short on the far end of this waveguide and collect both the directly emitted and reflected power. But some of our Project A collaborators pointed out to us that this was something that they had tried at the very beginning of their experiment. But these RF amplifiers are actually a source of white noise, and they ended up exciting a couple of cavity modes that would destroy their sensitivity at when you got to the when you had your electrons on those cavity resonances. So instead, we opted for a double-ended experiment because we have the space in the waveguide here. So we're taking the directly emitted and we're taking the wave that comes off to the left and the wave that comes off to the right, digitizing them separately after mixing them down with this 18 gigahertz analog down mixer. As I said, running it into the Roach 2 and spitting out FFTs, and then stacking those FFTs up into a spectrogram and trying to identify the lines inside there. So that's kind of what the experiment looks like in principle. This is a little bit more of what it looks like in practice. Like I said, the whole thing is based on this cylindrical waveguide into which we pump radioactive gases. Around that waveguide, we wind some magnetic traps so that we can confine the electrons after the decay events happen. And there's this U-shaped bit of WR42 that leads back to these low noise amplifiers and the Roach 2 backend. So as crazy as it may look, the whole thing actually works. This is sort of the first signals that we managed to get off of the instrument as of about 2 or 3 weeks ago. And I hope this is big enough on all of your screens that you all can see the diagonal lines here that represent these electron tracks. So each line is the track of a single particle radiating microwaves as it undergoes the cyclotron motion in that magnetic field. And you'll remember that since the energy is in the denominator, as the electron radiates away its energy due to microwaves, the cyclotron frequency actually goes up. So these are all individual electron tracks. And now we get the fun part really starts where we get to automate our algorithms for identifying tracks and making this into a coherent beta spectrum. So yeah, that's about all I can cover here in about 10 minutes. Like I said, I'm really honored to be here with you all. Thank you so much for having me. With that, I guess I'll take any questions.
Awesome. Thanks so much. I'm thrilled that you're here as a high energy physicist. I love high energy physics. Many of my friends are high energy physicists. And I will say,
it's an interesting.
Go ahead.
I was just going to say it's an interesting field to be in. I guess, we've been trying to break the standard model for many years, and now it seems like we might get it.
Yeah. I was just going to put in for good measure. The first time I went to this conference in 2019, I similarly felt like I had no idea what any of the terms meant. So I just want to let you know that it gets better. It is helpful to rewatch talks.
Yeah, definitely.
Okay, so I'm monitoring the chat to see if anyone has questions.
Okay.
In the meantime, so I'm familiar with the G-2 result because a lot of my friends are high energy physicists, but I think it might be cool just to talk about that a tiny bit if you have time to share like the major results and what it means.
Yeah, I mean, so I guess for the uninitiated, there's this standard model prediction for the anomalous magnetic moment, essentially the magnetic strength of the muon, which is this particle that participates in the weak interaction. And you know, being high energy physicists, we're very interested in these questions of fundamental symmetry. And there were theories of physics beyond the standard model that predict a different value for these for this anomalous magnetic moment of the muon. And they went and measured it at Fermilab after the Tevatron was decommissioned. They kind of were looking for something to do with the machine. And there was this old Brookhaven result that was about, I think it was 2.5 sigma away from the standard model value, which is kind of right on the cusp of where you don't want to be, I guess, in terms of staking a claim to have seen something that is real. And so the Fermilab folks sort of reconstituted their experiment, the old Brookhaven experiment, in the muon hall at Fermilab, and managed to measure a value for this muon anomalous magnetic moment that I think was 4 sigma away from the standard model value, which is really sort of not quite the threshold for a discovery, but definitely getting there. So this really would be kind of the first result in particle physics that would directly undermine the standard model. And it just so happened that it happened in the context of this of the weak sector physics, which I think is particularly intriguing as somebody who studies beta decay.
Awesome, thank you. There is one more question. I think maybe if you go back to slide 6, that will be the best
okay.
Visual.
Yeah.
Awesome. Okay. So someone asked if you could, if your experiment could benefit from a higher bandwidth, or if 2.5 gigahertz is enough. And I'll kind of extend to say, like, I think it would be interesting to know when you're saying we want to make a measurement that's sensitive enough to 10 to the minus 4, what are the main noise sources in this that you have to get rid of? Is any of it related to the readout, or is it more sort of like that white noise that you described from the amplifiers, or what will be the main challenges in meeting that?
Yeah, I guess most of the noise is thermal. You know, we want to keep these amplifiers at liquid helium temperature so that we can keep a decent signal to noise. We are definitely interested in maximizing the bandwidth up to the point where the next highest order mode of this particular waveguide kicks in, because that kind of adds a little bit more hardware complexity. You know, having the signal to noise to observe Krypton events is actually pretty good for us, because the Krypton metastable internal transition is fairly low energy compared to the helium-6 beta decay. And so the helium-6 electrons will have more kinetic energy and therefore more RF power for us to observe. So this is really kind of pleasantly surprising that we were able to observe this to begin with, because if we have the signal to noise to observe Krypton in this apparatus, then the helium-6 events might actually be a little bit easier for us. But yeah, we definitely want more bandwidth, because this is kind of a full spectrum measurement, and in every decay. Every decay sort of counts for our results. We're not sort of interested in the precise location of this endpoint like you would be if you were trying to study tritium decay to set neutrino mass limits. So we want to sweep up about a total of about 10 to the 8 events in total to get a sort of a high precision measurement of the distortion, any potential distortion to this spectrum here. Hopefully that answers your question.
Yeah, I think so. Let's see, we have 3 more minutes, so maybe time for one more question. I have lots of questions I can ask. I guess maybe just one more thing to clarify about the slide is it looks like there's a 300 Kelvin, the red thing coming from the turbo.
Mm-hmm.
And then the RF amps are at 5 Kelvin. So where are these things entering into some sort of cryogenic setup? Is the actual cavity cryogenic?
Yeah. So the decay cell itself is at about 100 Kelvin, which is about as low as we can get before we're freezing out our krypton calibration source.
I see.
This whole thing is in a vacuum can, and we did a lot of work to try to make sure the cryogenics would make sense. The main cryostat here is outside of the magnet region. And the input of this helium pipe here is at room temperature, and we're just relying on the thin wall titanium pipe here to get you from 300 Kelvin to 100 Kelvin, and then a bunch of insulation. There's some thermal breaks in here that we specially engineered to get us from 100 Kelvin down to 5 Kelvin without pumping too much heat into these amplifiers.
Awesome.
Yeah, I guess the cryogenics were, I mean, the fact that worked too was kind of a big relief. It was very much down to the support of the expert engineers that we had at SEMPA. So we're very grateful to them.
Great. Well, thanks so much for coming and telling us about your experiment.
Yeah.
Next, we have the last talk of this session. Will be by Kathryn Plant, who's done an amazing job planning this whole conference. Kathryn is a graduate student at Caltech, and she'll be talking about a SNAP-2 cosmic ray detector.
Thanks. Sorry, I'm just sharing making sure I shared the right screen. Do you see?
Yes, got it.
And the slides, not the presenter view.
Yes, the slide.
Okay, cool. Yeah. So I'm a graduate student at Caltech, working with my PhD supervisors are Greg Hallinan and Andres Romero-Wolf. I also work a lot with Jack Hickish, and I'm going to talk about a high energy cosmic ray detector that I'm building for the Owens Valley Radio Observatory long wavelength array. So first, I'll outline an overview of cosmic ray science that I'm interested in, and then I'll describe the detector that I'm working on. So this is a 73 megahertz image from the long wavelength array, and this is a very different signal processing picture than what I will end up using for studying cosmic rays, but I wanted to start with this as an overview because at 73 megahertz, most of the light that we see is synchrotron emission from galactic cosmic rays. And you can see this tracing out the large structures in the ISM. Cosmic rays are high energy charged particles, such as electrons and also atomic nuclei. And they're traveling close to the speed of light. And because they're charged, they turn around magnetic fields, which is why we have the synchrotron emission. Even though these relativistic particles are spatially diffuse, they contribute comparable energy to the interstellar medium as thermal pressure and magnetic fields. These high energy particles are one of the really important links between how extreme environments like supernova remnants influence the conditions and evolution of a galaxy as a whole. Since they turn around magnetic fields, we can't trace their arrival direction back to a source. And so we have to study them from the sample of cosmic rays from all directions as a whole. And this plot is showing an energy spectrum of cosmic rays all the way from lower energies where we can detect compositions of individual events with space-based detectors, down to in blue are data from high energy experiments that need to be conducted from the ground in order to have a large enough collecting area. And so this power law spectrum is nearly the same power law over more than 10 orders of magnitude in energy, all the way from where there are hundreds of particles per second per meter squared, down to at the highest energies, maybe only 1 per kilometer squared per millennium. So for those, you need to cover really large areas of ground to detect them. And this orange arrow at the bottom is just indicating the highest energy that the proton experiments at the LHC reach. And so beyond this, we're into a region that for now we can only study with particles from space. So I want to know where these cosmic rays come from, and up to about a peta-electron volt or a few tens of peta-electron volt, these could all be accelerated in shock waves in supernova remnants within our galaxy. And at the very highest energies, they're thought to all be extragalactic, most likely from jets from active galactic nuclei. But there's this energy region in between these classes of sources where it's not thought that AGN jets would produce enough cosmic rays to describe everything that we see, but it's also not thought that supernova remnants can quite get to that energy. So there needs to be another type of accelerator. It should be within the galaxy, and conveniently, this is the energy range that arrays built for low-frequency radio astronomy can study. So this green bar shows energies, highlights energies that would be observable with the Owens Valley Radio Observatory long wavelength array. And again, we have to study cosmic rays at this energy range from the ground because we can't put a many kilometers size detector in space. And so since we're studying it from the ground, we can't actually observe the original particle. What we observe is the aftermath of that particle's collision with the atmosphere. When it first hits the atmosphere, it triggers a cascade of particle collisions, and all of these high energy particles, because they're charged, they're turning around Earth's magnetic field, and they emit a pulse of radio emission. Since the shower is developing very close to the speed of light, an antenna on the ground would observe emission from different parts of the shower at almost exactly the same time, because the shower itself is traveling almost as fast as the emitted light is traveling. So if you populate a region of the ground with antennas, they would each observe roughly 10 nanosecond pulses. And this is what I want to detect. So I'll be using the Owens Valley Radio Observatory long wavelength array, which was originally built for more traditional astronomy, like that map that I showed at the beginning, including epoch of reionization science and extrasolar space weather, solar flares, as well as stellar flares from other stars. And in the previous version of the array, there were 288 dual polarization antennas. This is being upgraded to 352 antennas and baselines up to 2 kilometers. And as part of the upgrade, all of the first stage signal processing will be done by 11 SNAP-2 boards. And I'm going to build a cosmic ray detector that will run on the same SNAP-2s as the F engine and run alongside it, observing for cosmic rays all the time. With the previous stage of the array, Ryan Monroe, who was a graduate student before me, detected 8 cosmic rays in a 40-hour observing run. For this, he had to reprogram the Roach 2s with special firmware, and so a big part of the upgrade is that I'll make something that can run alongside everything all of the time. But here's a snapshot from one cosmic ray. So the signal at each antenna in the core of the array is going to be plotted as a spot size that increases with power, as well as color showing the power. And then each spot is at an antenna position. And so you'll see the cosmic ray wavefront kind of sweep across the array. In order to detect these events, I'm going to buffer 20 microseconds of data and then only send these 20 microsecond snapshots out of the SNAP-2s when there's been a candidate event. And so within each SNAP-2, which there will be 64 antennas going into each board, and each SNAP-2 will look for coincident pulses within the 64 antennas that it supervises. And then if there's a coincident pulse on a threshold number of antennas within the light travel time for those antennas, the SNAP-2 will transmit its buffer over Ethernet, and it will also send a signal so that all the other boards, even if they didn't detect the event themselves, all the boards will send their data and we'll get a snapshot from the whole array. I need to do this communication between the FPGAs very quickly, and so I'm using the general purpose input-output pins and just connecting a wire from board to board. On the right, I just have a little schematic of what the receiving software has to do. So it takes individual packets that have a subset of antennas and time samples from an individual board, puts that together with the rest of the snapshot from that board, and then assembles that with the snapshots from the other boards to get something from the whole array. And now the time that it takes to read out that snapshot has to be slowed down enough that the receiving computer can get data from all 704 antennas into one computer for the next stage processing. And so I had to slow down the readout time to about a millisecond per snapshot so that the data rate from the whole array will stay under 25 gigabits per second at the receiving computer. And now when I am reading out the snapshot, I'm not continuing to observe. And so to minimize the dead time, I need to minimize the event rate. The real cosmic rays will only be about 25 per day. And so the data rate for real events is very low. But in the previous experiment that Ryan Monroe did, there were about 500 RFI events per second. I need to not saturate the, and not use all my observing time just reading out data. And so I want to keep it to about 50 candidate events per second. To flag the RFI that has to be flagged on the FPGA before sending events, I'm going to use the fact that a real cosmic ray only illuminates a limited area. So in this plot is a simulated cosmic ray event overlaid on the core of the array. So the color corresponds to peak electric field, and all the antennas that are highlighted in red would detect this event. So clearly it's important that neighboring antennas are processed by the same FPGA. But then also I can use distant antennas to flag RFI, because RFI will sweep over the whole array and not have this beamed emission pattern. And so each antenna, or each FPGA, will have a group of neighboring antennas and then a few distant antennas that will veto RFI events. And this map is showing how antennas will be plugged into FPGAs. This is a quick overview of the planned classification pipeline. And I don't have a lot of time to go into all the details, but after snapshots have been received from all the FPGAs, I'll check that the wavefront shape is and power distribution is what is expected for a cosmic ray. And so I'll just discard thermal coincidences, flag directions that are known RFI sources, and also cluster events in time to rule out airplanes, because we have RFI reflection events off of airplanes. And then finally, the spatial power distribution and the polarization will confirm the real cosmic rays. And just to go over a summary of the instrument I've described, we have a needle in a haystack problem going into the FPGAs, where there are about 500 RFI events per second, but only 25 cosmic rays per day. So there's initial RFI flagging on the SnapTwos. Then buffered snapshots for good candidates are sent to a computer and processed to find 25 cosmic rays per day, from which I'll be able to construct some arrival direction and composition information that will hopefully help start to elucidate cosmic rays in this energy range that is from an unknown galactic source. Thank you.
Awesome, thanks. I've got a couple questions. There's a break next. Nominally beginning in 3 minutes, but I'm sure we can go a little bit into the break, and anyone who needs a break, obviously just feel free to take it. Okay, so first, a quick question. Are the simulations done using, I'm not sure what this is, COREAS?
No, these are from ZHIRAS, but there's been a lot of comparisons that ZHIRAS and COREAS get very similar results.
COREAS, okay, thank you. Teach me how to say that. Okay. Another question, I have the same question actually, is could you tell us a little bit more about how the trigger is working?
Yes, so right after, so the raw ADC samples will be buffered, but then in a parallel stream, they'll go through just a simple filter and thresholder that looks for pulses above a threshold power level. And then that pulse will be extended according to the light travel time for the group. And then I'll just sum across the extended Boolean pulse or no pulse signals for all the antennas. And then if that sum is above some threshold number, then threshold number of antennas have exceeded the power threshold within a time window, and that indicates a candidate for a impulsive event. And then there will be an additional delay where I wait for the light travel time out to the veto antennas, and then if the veto antennas don't see anything but the core antennas did, then that counts as a event that should be triggered, and the board will stop writing new data to the buffer. It will read it out over Ethernet, and it will also send a signal to the board next to it that board should do the same thing. And then that trigger signal gets passed around a loop of boards.
Nice. Is that a lot of data that you have to buffer? Is that a challenge, like managing storing that, or is it not actually that difficult?
It fits all right on the FPGA. We couldn't buffer a huge amount more than this, but 20 microseconds shouldn't be a problem.
Okay, cool. This specific question asked if it was a radio self-trigger.
Yes.
Okay.
So that's one of the cool things I meant to talk a little more about this experiment is we want to be the first observatory that is using radio self-triggers to decide when to save data, as well as using only radio data for all of the classification and event reconstruction steps. And so a lot of other experiments have to, if I go back to a slide showing the particle shower, so some of the other particles in this shower also reach the ground. And so you can make scintillator panels that will detect, say, muons, and use that to know when there was a particle shower. But these muon detectors are a lot more expensive than a radio antenna. And so if you want to cover your whole detector area with muon scintillators, it is a much more expensive experiment. And so we are planning to get a few scintillators just for a small part of the core to verify that our trigger gives the same results as a more traditional method. But the advantage of having a radio-only method is you can build large arrays without needing to get scintillator panels.
Okay, great. Another question is asking about partial polarization in cosmic rays and asking if you could describe if the detectors study this polarization and how, and what are the, well, I'll let you answer that first and then I'll ask a follow-up.
Okay, so in the atmosphere, a large component of the cosmic ray emission is from charged particles in the shower turning around the Earth's geomagnetic field, and that component will be polarized according to the axis of the shower and the Earth's magnetic field. And then there's a secondary component. If I go back to the simulated shower, as you can see, it's not perfectly symmetric, and that's because there's a secondary component that has to do with charge buildup at the front of the shower. This is called Ascarian radiation, and it will have a more radially polarized component. And so the sum of these two components determines the polarization of the event. And so different antennas in the shower will see slightly different polarizations. And this is something that's a little more computationally intensive to check. We were basically going to compare it to simulated showers in models. And so we'll do that at the last stage of classification, where we've thrown out almost all of the RFI, and we'll just have maybe dozens of events per day, of which up to about 25 will be real cosmic rays.
Great. The follow-up was on the summary slide, you mentioned 3 key observables. What are these?
Oh, the arrival direction, the total energy, and then the height of the shower, which is related to whether it was a lighter or a heavier original particle. Okay, great.
Let's go through 2 more questions. I don't want to eat too far into the break, but I think we've kind of established information about the trigger, but yeah, there's another question about that you can maybe answer in the chat after this.
Okay.
Okay, so one is, Could FRB, fast radio burst detections, be incorporated, or would that have to be a mutually exclusive mode?
Fast radio bursts have about a millisecond duration, but the dispersion will sweep out the burst over a much longer time scale than what I'm looking at with this. So I think to look for fast radio bursts, you'd be better off dedispersing the F engine output that is could also be done with different signal processing, but not really the same cosmic ray firmware. But there's F engine firmware running at the same time.
Great. Okay, the last question is, what's the RAM usage on each snap 2 for the buffering? I assume that's the buffering we talked about with the triggering. Deepthi, jump in and tell me if that's not what you meant.
Yeah, so there are 4,096 samples times times 64 antennas, and then 10 bits per sample. And sorry, it's been a little while since I calculated that out. But it was, I have a separate slide I could have added with more details of FPGA utilization. So maybe I'll answer this in the chat.
Okay, great. Well, thanks so much everyone for coming to the morning session. I'm stepping down as chair as of now. But yeah, this has been a great talks today. Thank you to all the presenters, and looking forward to more discussions to come. Of course, feel free to reach out to presenters in the Slack. I think that's probably the best way if you want to ask follow-up questions or maybe schedule a one-on-one with someone. Thank you all.
Francois here. I'm just checking if there are any other presenters for the next session who want to test anything.
Yeah, this is Robert Anderson. Let me go ahead and try testing this out here. Let's see. Screen 1. There we go. Are you able to see it okay?
Yes. Yeah, I see your slides. You want to just launch that and check that it comes up in the full screen view?
Yes, yes.
Yep, that's right. All good. Okay, you are good to go.
Excellent, thank you. All right. I will start with a real-time demo running on RF SoC.
Right, and I'll give you a warning. We'll allow 5 minutes for questions, so I'll give you a 5-minute warning at 20 minutes.
Okay.
And then when we get, if you're still speaking 25 minutes in, I'll just say time, but you can carry on and give you an idea of where you are.
Sounds great.
Right, any other speakers who want to trial their presentations? we all good for the break?
Hello, Bela here.
Yes.
Hello. Bela here. I
Yes,
want
Bela.
to take my presentation.
All right.
Yeah. We'll share. Yeah. Oh, yeah.
Yep, that looks good. Just try to run it so we can see it goes full screen. Bela, I have a black screen.
I think it might be your internet connection, Bela.
It's look okay.
I have only a black screen.
Oh, okay. Okay, okay. Oh, okay. Now? Hello?
Yeah, I can see your basically your workshop screen. Yeah.
Yeah, okay. Oh, this. Now presentation is visible?
See the presentation? Yes, that works.
Okay, thank you.
All right. Bela, your audio is a little bit on the iffy side, but we'll see how we can go. And if any problems appear, then we'll just deal with it then.
Yeah, thanks.
Thank you.
Thanks.
Franco, can I try out my pre-recorded video?
Yes, are you going to play it from your machine?
I want to see which is better from your side or my side. I'm going to try from my side now.
Okay, give it a go from your side.
Can you see the screen?
Yes.
All right. Does that look good?
Looks good. Just play it so we can check the audio. I don't think we're getting the audio. Did you tick the little block that says share computer audio?
Okay, let me try it again.
As you share the screen, there's a tick box.
Yeah, okay, that and that too. Okay, I'll try that again. So if I go play again. Hi everyone, I'm Mathews from Sarajevo in South Africa.
Coming through.
Oh, okay.
There are
Did you see
two black boxes across the video? Is that also so on your screen?
No, I don't see.
It's probably your Zoom participants in chat. You can just minimize it.
Yeah, the black boxes are usually other applications.
There we go. Yeah.
Is it okay now?
Now it's fully visible. Yeah.
Right, so do you want to play it from you want me to play it from my side or your side? Maybe.
What's the feeling? Did that work okay? Are we going to try that?
I just want to see how it feels like from your side.
It was fine from my side. I'm more checking in with the tech support team. They were happy.
Did it look a little bit fuzzy?
Okay, so that's fine. You can.
We can try it to play on our side if that's what Matthew wants.
Okay.
Yeah.
Okay, so why don't we try it on our side? See.
Yeah, give it a go.
Okay, you're me, Ryan.
Hi everyone, I'm Mathews from Sarajevo in South Africa. I'm going to present the application of the AXI interface in the Casper Toolflow.
It's very little to judge on, but I think that worked a little better. So let's go with that.
Which one? The earlier one?
No, the second one, Ryan playing it.
Oh, okay, all right, that's good. No problem.
Okay, so we'll play it on our end then.
Yeah.
Yes.
Thank you.
Yeah.
All right, we're 1 minute away from starting. Robert, I think if you want, you can share your screen so long. Get ready for the start. See if we can be on-time start and hopefully run into an on-time finish.
Yes, absolutely. Right, let's see. Okay. Want to show the actual hardware.
Okay, Robert, while you're setting that up, let me just introduce you. It is 6:15 in South Africa. So I think an invited talk from MathWorks is very appropriate. A great deal of the FPGA stuff that you've seen about that's been implemented using MathWorks tools. And so we're very grateful for all that they've contributed. And with that, I'll hand over to Robert. I think there's going to be some demonstrations here, so I'm looking forward to seeing that. Take it away, Robert.
Hello, everyone. I'm hoping you can hear me okay. And thank you very much for the invitation. I really appreciate being able to spend time communicating with such a community. So what I would like to speak about today are MATLAB and Simulink MathWorks HDL code generation workflows and some of the efforts, that MathWorks has been putting in over the last, 15 years or so to bring an effective HDL code generation and verification workflow to you. So I wanted to start by showing you some work that we've done over the last few years on one of the many platforms of interest, and this one in particular is the ZCU 111, the RFSoC board. So what I just showed you was a demo basically of a 512 point channelizer that is currently running live in real time on this RFSoC. And this particular workflow is enabled through HDL Coder and obviously through Vivado IP Integrator. The demo itself is fairly basic. It's let me go ahead and show you the kind of the source Simulink model here that's running this. Now, in this case, the way that I'm using the RFSoC is I'm actually transmitting a signal out onto the digital to analog, one of the digital to analog converter channels, looping it back through the balun, which you can see here. I have a single loopback cable on the balun connector to the ZCU111. That's essentially looping that analog signal back. And then, of course, we're digitizing it, and we're bringing it in via one of the RF tiles, tile 0 in this case, and then we're running some processing on it. So before I jump into too much detail on this, let me show you some things about the presentation here. Actually, let me go a little bit further and I'll just go over. So this is what I'd like to talk about today. I know I don't have a ton of time. I just showed you the demo of the high-speed channelizer running on a ZCU111. This channelizer is only 512 bins, but you can actually extend out to 128,000 bins, not just for channelizers with polyphase branches, but we also have similar very high performance Fourier transforms, FFTs, that you can extend out to 128,000 channels as well. So I showed you that. So the next thing I'd like to talk about is how then you can use MATLAB and Simulink and capabilities known as HDL code generation through HDL Coder, which is very similar in a lot of ways to Xilinx System Generator, but it's a dedicated product that MathWorks has been developing for a large number of years now. One of the key parts of this does include floating to fixed point conversion. I'll speak about that a little bit in the way that we have direct integration within our data path for a rather elegant way to very quickly allow you to do a transition from idealized floating point, which of course MATLAB and Simulink default to, down into a fixed point representation. Along those lines, I do want to make it clear that MathWorks has put a lot of effort into creating floating point, well-supported floating point data paths as well. And there's I guess you'd say a sort of a nice, elegant coexistence between floating and fixed point constructs that you can use within your data paths. There's optimizations as well. And then of course, RTL code generation. All of the code that HDL Coder generates is generic, register transfer language, Verilog or VHDL. So it's not, these are not gate level net lists. They're very readable. You can, easily cross probe between your source code and the target model. And then of course, deployment path of the algorithm onto a whole variety of commercial off-the-shelf and custom evaluation kits. And then, of course, communication between host and this FPGA object that I was showing you earlier. And also I want to mention MATLAB and Simulink in the cloud. We do provide some ability, I'll go into this at the very end, where you can put these in containers through Docker. Right. Let's see, let me go back. So what are some of the requirements for this flow? One of the things we really want to make clear to you is the idea here is we want to give you an infrastructure, and I guess I would call it the surrounding plumbing, to allow you to focus your development efforts more on the algorithmic IP versus having to spend a bunch of time on the infrastructure, the development infrastructure around it. The more we can do at the high level in terms of modeling, of course, it's much easier to traverse the design space. Contrasting that with having to do very low level, hand manipulation of RTL and place and routing thing, it can get very challenging to traverse the design space if we have to do stuff down here. So our hope is give you a way to exercise your models, do your design space exploration on your models at a higher level before you have to go down and transition into the lower level HDL. So the typical prototyping workflow that MathWorks provides, allowing you to start by creating your high-level model using Simulink and I would call equivalent constructs HDL coder blocks that you can generate, Verilog and VHDL4. And then, of course, in this scenario, integration with the RF tiles on RF SoC. Currently, what I'm showing you, what I showed you earlier is the ZCU111. MathWorks also provides some direct support for the ZCU216. The other piece of this is hardware-software co-design, where we not only can you generate Verilog and VHDL from your Simulink models and your constructs, but you can also generate C code. Now, the model that I showed you, let me go back to that, and then the notion of being able to very quickly and effectively collect data and instrument these models. We have a variety of mechanisms that will allow you to instrument. We've got a direct connection to an AXI interface, and then through libraries known as libIO, that's kind of the libIO are a set of utilities that MathWorks developed on a number of years ago that give you very efficient communications directly from AXI interconnect into your host, whatever the host is that's connected, whether it's MATLAB or something else connected onto your hardware object, in this case, the RF SoC. So the model that I just showed you is running this 512 bin channelizer, kind of sweeping a tone from 1 megahertz up to 1900 megahertz in 10 megahertz increments. The basic elements of the workflow are obviously starting in a high-level algorithmic modeling environment, running your simulations the way that you typically do using MATLAB and Simulink. And then, of course, depending on your notion of how you would like to partition between hardware and software, i.e. the stuff that you want to target to the FPGA fabric versus the items that you would desire to stay in the software, the Cortex A53, some sort of partitioning exercise. And then, of course, floating to fixed point conversion these are key parts of this section of the workflow. I'm going to jump over into the model because I want to show you some important aspects within the model itself. All right, here we go. So this is the polyphase channelizer model. So this is an output path from the digital to analog converter, feeding back around to the analog to digital converter input in the channelizer. This is test bench. So this stuff at this level, these registers are test bench. This is data collection. So this model will run right within Simulink. I can run this model. This is not the hardware object. This is the starting point. And then I will show you very quickly how you can go through the workflow to turn this into a hardware object that then runs on the ZCU111. Now, before we do this, I want to show you some things about the model itself. This is the guts of the channelizer. So this object here, this is an HDL optimized channelizer that was developed by MathWorks. From this, you can configure the number of bands on the FFT, on the FFT, and then of course the polyphase branches, configurable up to 128,000 elements. This particular one that I have is set for 512 elements, 512 bins. So very, very configurable. We provide mechanisms for being able to run DMAs and run transfers from the host processor, the Cortex A53, down into the FPGA fabric very quickly and efficiently. So this is an FPGA capture block that's used for snapshotting just a portion of, you know, this incredible amount of data that's coming in off the analog to digital converter. So the analog to digital converters on the receive side here are configured to run at 4 gigasamples per second. And we're running the channelizer in a mode where we are chunking in a vector of 16 elements at a time. This is configurable, so you can run the channelizer as well as HDL optimized FFTs, either bringing in scalar values up to, in this case, we're running 16 elements per chunk. So these are very nice architectures that give you a lot of flexibility in terms of determining you know, how fast you've got to be able to bring your data in order to facilitate the processing. Let's go further. So those are some key things about the model that we are targeting for HDL. So all of this stuff that we're looking at here within this polyphase channelizer block, this whole block, we will be generating HDL code for. Now, I've already done it in the interest of time, but what I'd like to show you next is our workflow advisor. Now, again, as I mentioned, this workflow, you know, this is distinct from Xilinx system generator. It's similar in a lot of ways, would say, to Xilinx system generator, which it sounds like many of you are quite familiar with already. But a key difference is we all of this code that we generate is generic register transfer language, so it's quite readable. Now, regarding the plumbing, let me show you a couple of other items that you may find quite useful. Not only are we generating the HDL code for the guts of this thing, the internals of the polyphase channelizer block in this scenario, but we are also directly utilizing Vivado IP Integrator through, I hate to use a bunch of jargon here, but through the MathWorks IP core generation workflow. So this is a little bit distinct from generic ASIC and FPGA generation, where you're just generating either Verilog or VHDL for your target design. IP core integration, IP core generation workflow. What this gives you is it also gives you access in this scenario to an underlying reference design, which enlists this plumbing and a software infrastructure that MathWorks has already developed for you. So the idea is, now these models are free, by the way. We don't charge, there's no royalties involved. When you use HDL Coder, any of the code that you generate is yours. Any of the code that you are using from MathWorks, these channelizers, the FFTs, all that stuff is free. It's all very readable. We don't charge royalties for any of this stuff. I know in the past there's been some questions that have come up regarding how does the MathWorks framework really bolt into, say, an open source environment. Although for commercial use of the tools, we do charge for these, but from the university perspective, you've got access to all these tools already. We've been talking internally for those who may have challenges getting the tools. We are talking internally about ways that we can make it much easier for you to gain access to this kind of tooling. If you're having issues, if you are having issues, please let myself know or let Temo know. And we very much would love to work with you on this kind of tooling. So regarding this underlying reference design, we have various reference designs that we've already developed internally that target the RF SoC. We don't just target ZCU 111. MathWorks targets a whole variety of different commercial off-the-shelf evaluation boards. If you have custom boards as well, we have a published framework that allows you to target any sort of board that you might have if we're not directly targeting it today. It's a published workflow, basically. If the board you are targeting is already recognized and registered within this IP core workflow that I've been talking about, what you get is immediate visibility into all of the I/O that's associated with your model. In addition to this, MathWorks will generate sort of the underlying configuration framework that you need for defining the sample rates you're using on the RF tiles, the relationship to, the board level PLL, this very high precision reference clock that's running on the RF sock that some of you may already have quite a bit of familiarity with. We also have visibilities built in, so you can connect in for test point visibility directly into the AXI interconnect, a way to monitor test points and then view them via JTAG, or actually view them through top-level gigabit Ethernet interface, which is part of what I'm actually running, what I ran earlier.
Robert, 20 minutes.
Okay, great. Thank you. Let's see. I just want to be sure I hit all the highlights here for you. So you can see what we're up against here. All right, so we talked about the channelizer, the modeling, the generation of Verilog and VHDL. One other key part of this workflow is the ability to provide you direct interconnect with AXI for both memory mapped interfaces as well as streaming interfaces, and then direct memory access for external memory. We provide you all of the infrastructure for doing that. And that's what enables this particular model that I was basically showing you earlier. The hope is that you can use stuff like this. And I know in the other talks that I had heard earlier, clearly these higher precision FFTs may be of vital importance to some of the work that you're doing. We would really like to work with you on showing you how you can use some of the MathWorks IP for either channelizers or FFTs or the like in order to provide you the resolution that you desire. All right. See, regarding the target interfaces, if you are targeting these, these boards that IP core workflow have visibility into, this gives you a direct mapping into the different kinds of interfaces. So these interfaces described here are the exact same I/O that existed on the top level Simulink model that I was showing you during the beginning of the presentation. So you can select the kind of interface that you would like to run, if it's AXI4, if it's AXI streaming, whether or not you are trying to target and map directly into an RF tile, receiving off the analog to digital converter or the like. So the hope would be with this framework, you could get a model up and running in just a couple of hours on using this particular workflow. Let me just show you within Vivado. So in this particular scenario, this model contains the converter tiles, and it contains the the processing subsystem, as well as the MathWorks specific IP. So this is a piece of interest that you use HDL Coder to generate. This is how it got directly integrated through Vivado IP Integrator, using this workflow into the Vivado IP Integrator environment. We did that for you essentially automatically. So it's a very powerful workflow. It provides you a lot of flexibility. There's associated verification frameworks that do go along with this. Obviously, I didn't spend a lot of time talking about this stuff today, but we do things like generate system Verilog as well. These are all, and this is all stuff you can basically export out of the MathWorks framework and use in your event-driven simulation frameworks, whatever those are. Whether it's Cadence or Quest2Sim or Vivado, the simulation environment that Xilinx provides. All right, and then one last thing I'd like to mention that I know was quite important and of interest to the community here. MATLAB and Simulink are now available in the cloud via Docker containers, and this information is directly available to you. So via the Singularity containers here, you have direct access to MATLAB and Simulink in the cloud. All right.
Great, thanks. Are you finished?
Yeah, that's pretty much it.
Okay.
Any questions on this?
Spot on time, right at the moment I was going to interrupt you. So I don't spot any questions yet in the chat, but I have a question. Yes. MathWorks produce a bunch of code generators, and the HDL one is the one that you focused on today. But you can also generate C code, and you can also, I believe, target GPUs via CUDA, I think. Are there any ideas of integrating those, to target heterogeneous platforms where you could have one design with a component in an FPGA, a component in a CPU, or something like that?
So we do that today with this particular hardware-software co-design workflow. We do facilitate that today. So I kind of focused on the HDL code generation workflow, but we do generate also C code for any of these models that you can generate Verilog or VHDL for. You can also generate C code for embedded targets. And right along with that, and I should have put a slide in on that, given your focus on GPUs. MathWorks has it's been a product for roughly 5 years now, GPU Coder, where we do generate CUDA type code as well. So that absolutely is a key part of the workflow, and we have direct abstractions available for being able to communicate between Cortex A53, these SoC programmable SoCs that you are using. We don't have necessarily abstractions today for a GPU coder into that environment, but we are looking into it. So it's not in the product today, but that is a key part of the work that MathWorks is doing to directly incorporate this. Yep.
Great, thank you.
Yeah.
More questions popping up now. Can we run those cloud containers in our own Kubernetes cluster?
My understanding is yes. You can run it as a Singularity container. We can talk about this more offline if you would like. But that's the idea, is that you can take it as a container and run it on your own.
Thank you. Next question, what is included in the cloud containers? Any toolkits, any with system generator integrated?
To my knowledge, not today, not within the containers. But let me see, I will get more information on that to see if we're looking to extend what is currently supported within those containers. If I will mention that if you do have this workflow, the HDL coder workflow provided by MathWorks, which by the way, is directly available to all of you. All of this tooling that I showed today is available via university licenses. You know, Berkeley's obviously got these. So my understanding is the majority of your community does have this tooling directly available today. Yeah, so you should have direct access to that, not necessarily through the containers though.
Okay, great. I think it's time to start switching to the next speaker, but thank you very much. That's very interesting, and I enjoyed that. Our next speaker today is Mathews Chirindo, and Mathews will be presenting via pre-recorded video, which we'll play for you. But Mathews is online, and Mathews, I'll ask that you just watch the chat window, and if questions pop up, you can just start answering them straight away.
Hi everyone, I'm Mathews from Sarajevo in South Africa. I'm going to present the application of the AXI interface in the Casper Toolflow. Just an overview of what I'm going to present. I will present the background of the AXI interface. I will try to motivate why the AXI interface is probably preferred in the Toolflow. I'll look at some principles of the AXI interface. And most importantly, I will present the AXI interface in the Casper Toolflow application. I will show you some references and point to you where the documentation for the AXI is found. And if there are any questions, they can be asked at the end. Just some background here. The communication between the processing system and the programmable logic is achieved through the AXI interface, in some cases, such as the Xilinx Zinc system on chip. So the AXI interface is not the only interface for this purpose. There are other common system on chip interfaces, such as the processor local bus or on-chip peripheral bus provided by IBM. There is the Wishbone, which is part of the OpenCL codes. Just to motivate why the AXI interface may be preferred in the Toolflow, I'm going to look at some strengths of the AXI over other protocols or specifications, and particularly Wishbone, because Wishbone is also used in the Casper Toolflow. So the AXI was created for high performance, high frequency designs and suitable for high speed interconnects, while the Wishbone was created to provide common interface between IP cores, and that promotes design reuse. The AXI has separate address, control, and data channels, and that probably accounts for the high-speed interconnects also. And the Wishbone has different interconnects, including the shared bus. The AXI supports out-of-order transaction capability. Not sure if Wishbone does. The data bus width for AXI goes up to 1024 bits, and it goes up to 64 bits in the case of Wishbone. There is fast application of the AXI in the Xilinx fighters development flow, and that seems to be the future in my view. There is no Wishbone in this particular case, but it may be found somewhere else. So just some background of the AXI there. The AXI stands for ARM Extensible Interface and comes in AXI 3 and AXI 4 specification. It is a parallel high performance multi-master multi-slave communication interface that is mainly applicable to system on chips. So as you can see here, the AXI is derived from the advanced microcontroller bus architecture, along with APB, AHB, and ATB. If you want to know the meanings of these acronyms, you can refer to the bottom left corner here. So the AXI comes in 3 variants: the AXI4 memory map, we have the AXI4 stream, and we have the AXI4 lite. So it is important to point out here that the AXI4 lite is actually the AXI without the stream. So the AXI4 lite does not have the streaming functionality. The AXI supports point-to-point communication, that is, the master communicates directly with the slave, where the master initiates the transactions and the slave responds to the transactions. So the AXI master writes transactions to the slave, and it also reads transactions from the slave. And that is applicable to a one master, one slave situation. There are cases where you have one or more masters and one or more slaves, in which case you need the AXI interconnect to do the arbitration, to route the data from the master to the correct slave. Some AXI4 lite transactions, these are realized in 5 channels that exist in the read transactions and the write transactions. So in the read transactions, with the read address channel, you have the read data channel, and you can see the direction of the address there and direction of the read data there. In the write transactions, we have the write address channel, we have the write data channel, and we have the write response channel. There is also some AXI4 lite signals which are listed in this document here if you follow this link. And you must also remember that AXI4 lite protocol supports handshaking. So there is response signaling, which shows whether the transaction has been successful or not. And write strobe signaling to show which bits of the write data are active. So all this is found on this link here, if you follow this link. AXI4 lite, custom AXI4 lite interface. So this is what actually exists in the Toolflow, and the Casper Toolflow AXI4 lite slaves and the sysblock, the software register, the block RAM, the raw AXI register. And this is best explained with an example Symlink model. So this is one that I've just brought here with some software registers there and the BRAM there. The sysblock is not shown here. It does not need to be shown on the model, and raw AXI register can be shown, it's just not shown there. Yeah. So this is an overview of the actual application of the AXI4 lite interface in the Toolflow, where on the left-hand side here, that's where the processing system is. And you can see the advanced microcontroller bus architecture AXI there. And here we instantiate a platform that adapts a software interface which connects to the AXI interconnect. And here you've got the slaves. Here you have the sysblock instance, the software register instance, the shared VRAM instance, and the raw AXI register instance. So the existence of these slaves here is dynamic and depends on the number of blocks that you include in the model. But however, the sysblock does not need to be in the model. It always exists. And you need to have at least one software register in the model. It has been found recently that if you don't include a software register in the model, then that won't build. The AXI4 lite interconnect logic and all the XML to VHDL generated blocks, all these blocks here, they are all wrapped up in the AXI4 lite interconnect wrapper. And that exposes some ports here that drives or are driven by some Simulink logic blocks here and some other logic that may be defined in the FPGA fabric. However, the raw AXI is not part of the AXI for Light interconnect wrapper that connects directly to the AXI for Light interconnect, and the user must define his or her own logic in order for this functionality to work. Now, how do we instantiate these slaves in the Toolflow? So here's a class in the Python code called sysblock, and you call the function at top level top.x4light interface, and you pass these parameters here. You can see the memory map is also passed as an argument. And that's how you instantiate the sysblock. And the same applies to software register. You call the same function and pass these arguments here. The BRAM is instantiated by calling the same function and passing the relevant arguments. The raw AXI is also instantiated the same way, but you have to specify the AXI for Light mode as raw. If you don't do that, then you won't be able to instantiate the raw AXI register. The class name here must also match the tag of the raw AXI register Simulink block. And here are the references here. So this AXI documentation, which is found in this link here, is where all the documentation is found. And it is important to mention that this presentation was derived from the same document. The rest are other documents that were referred to during the compilation of this document and this presentation. Otherwise, that's the end. Thank you. I don't know if there are any questions.
Thank you, Mathews. And I see that the first question that did show up, you've already answered. So Andrew asked whether 40 gig E and other blocks, whether they do not have actually for light interfaces. And the response was it was tested on the Red Pitaya, which doesn't support that. Next question from Wesley. Oh, that's contributing to the answer. Okay, any other questions? All right, we running bang on schedule, and with no questions, we'll start to accelerate a little bit. But I think I'm going to go ahead with the next presenter because there's been a lot of interest expressed in this next talk on the Pacific Research Platform by John Graham. So John, if you can get your screen sharing up and ready, we can maybe start a minute or so early.
Yes, I can.
Okay, take it away.
All right, thanks. I'm John Graham. I work at UC San Diego on 3 National Science Foundation grants. The Pacific Research Platform, which was the first one, Chase CI, which is the cognitive hardware and software ecosystem cyber infrastructure, which brought hundreds of consumer GPUs to attach to the previously existing network. And then because they liked us so much, they gave us another grant towards the National Research Platform to figure out how we can scale this. And so we started out as the Pacific Research Platform. It was a pretty big platform, even in its start. And it was just disk-to-disk testing, mostly grid FTP stuff, but we quickly realized that we had so many big data centers doing large flows that we had to increase our testing of the backbone to make all the investments that the National Science Foundation had done in the cyber infrastructure for the science DMZs for all of these places actually work together. And so our goals were to move the average 5 megabytes a second to 50 gigabits a second. And so our first tool that we deployed was the perf sonar toolkit with the mad dash that does end-to-end testing or end-to-X testing, these grids, so we can analyze basically node graphs of the performance of the wide area network as seen by our endpoints. As we grew, we went international. So we have GPU and storage in Kisti in Korea. We have a Pacific region pool that spans Hawaii and Guam. We have the Western regional pool that's most of the Western United States. We have a Midwestern pool coming up, and we have an Eastern pool already in place. So we have these data lakes that are basically, they're Ceph stretch clusters. We have over 1.5 petabytes, or actually no, over 2 petabytes in the Western pool alone. And we just purchased 1.5 more petabytes, 7 nodes to distribute to the other pools to beef them up. To add all the GPUs means we were adding users. So what we had to do was create a user portal that allowed us to onboard users from any campus on the planet. It was the idea. So we use CI logon, their federated identity, and the Kubernetes refresh token system to provide that. And basically anybody with CI logon or even a Gmail can log into this portal, and then what? They're logged in and they can't do anything. They have to be given a role and assigned to a namespace. So you can be given a role that's a namespace admin and you can create your own, or if you're coming in with a group of people, you're just joining some other work group that's already there. And this kind of glues you together across all the nodes, across all the devices and services that we provide. This is the namespace manager. It's a web user interface. We have a minimum metadata standard because this is built into our reporting for the National Science Foundation. So every namespace is measured and monitored atomically. Every packet going through the wire, every bit going to the disk, everything is measured. And that makes it very difficult and very easy at the same time to make graphs. We started adding a whole bunch of services. Jupyter Lab was one of our first thing, Etherpad, Web Open Drone Map. We host our own GitLab registry repos. So we have free access to the CI/CD pipelines. We host our own secured Nextcloud file sharing system. We've created all kinds of crazy traceroute monitoring tools, and we have lots of different tools. Okay. Sorry about that. We get back to, don't you just love pop-ups? There we go. I'm back. No, I'm not. Sorry about this. Okay. Moving on, one of the other things that we use quite extensively is Netbox. We use this as our start of truth. We use Ansible to scrape all the inventory that we have in our giant, globally distributed cluster. And it basically allows us to know what's connected to what. We use LLDP in the switches and on the endpoints to figure out how they're wired dynamically. And if somebody moves a wire, Netbox knows it. Our GitLabs, I talked about our DevOps. This is extensively used in our platform. Just so you know, there's only 2 of us running this whole thing, so automation is key to our success. We also have a highly tuned Inmon traffic sentinel. Every single node in the cluster has SFlow installed on it, and it emits back to this central site. We also have SFlow feeding to us from PackWave switches on the backbone in California and in NicerNet in New Jersey, New York area. We also consume those flow information with Elastiflow, EKS Elastic Stack, and then Grafana dashboards measure everything. So here you see at the snapshot that I took this screen dump, we had 562 GPUs available, 551 in use. That's, you know, an average day when there's a paper due. Here is the reporting stuff that our boss Larry Smarr loves to do. I think he has a PhD now in Grafana, but it allows him to slice and dice and point out who's using what where. And so this is just you can see that giant block of kind of brownish red in the center. That's IceCube. IceCube uses our spare cycles in a scavenger mode. And so we don't have any spare cycles when they come around. IceCube and Open Science Grid both can flow workflows into Nautilus to scavenge anything that's not being used. So our utilization is way up there. But they're a low priority queue, which means anyone else that comes in with a higher priority just bumps them right off the node. You might wait a second, but they're gone. They don't care. They'll come back with 10,000 more. We also have this new Elastic Stack 7-node nodes connected to our backbone that are designed to ingest real-time telemetry from all kinds of network experiments. And one of the craziest things that we are doing now is the Sense AutoGoal Layer 2 integration. By using REST APIs, we can now trigger 100 gigabit a second Layer 2 paths all the way from CERN, Switzerland, down into DTN in UCSD. Next thing that we're going to do is set up the plumbing so we can use the 100 gig ports on the back of the FPGAs. And so we can stream data from any point to any point in a mesh. And so we can now compose FPGAs, GPUs, CPUs, machines, storage, and workflow engines seamlessly. We're using federation to stretch our reach further than one might have without these new Kubernetes tools. Admiralty allows us to do typical cloud bursting where one management cluster pushes workloads to Amazon, Google, and Azure simultaneously. Or you can have your own cluster doing some work and a secondary cluster. Or the one that we use is decentralized federation, where we're federating in a single namespace to another cluster. They agree on the relationship, and then they can in turn federate some other workflow back to us or to any other cluster. And so this can be easily deployed and rapidly torn apart. So these federations are very thin layers that bind Kubernetes clusters together. This is an example of one of the coolest federations that we have. The Expanse cluster is used in conjunction with the Pacific Research Platform and the Chase CI GPU cluster to do the smoke and wildfire detection workflow for the HP-REN wildfire camera network. So camera feeds are brought in through Expanse. They're pushed into the Chase CI GPU for doing the neural networks for smoke and fire flame detection. And then when they do have a geolocation of an ignition, they push that into the wildfire simulation mapping system, which produces web maps for first responders to go react to the wildfire that's in progress. Being in California, we're very, very aware of wildfires. The other federation we're doing is Admiralty to ARM cluster. We have an IoT cluster. The base of the tower has a Jetson Nano with a Google Edge TPU plugged into it that does the work for the machine learning part. That's gigabit Ethernet connected to 6 cameras up on the tower. And then we have a 48-core ARM master node and all these little IoT devices using K3S. And Admiralty can federate between K8S and K3S. So I can push things from my cluster into the ARM cluster. Oops, I think I missed a slide here. There's one other part of this. For building ARM containers, we have a federation for our GitLab instance that pushes the ARM-based containers it needs to build just by a tag in the CI file, the integration file. It will federate that work over to this 48-core ARM master node, compile the Docker image, and then return it to the registry. And then the IoT devices will pull that same image that was federated, built federated in the master node from the other clusters Docker, registry in GitLab.
John, 10 minutes.
Okay. I think I'm done with my major part, except for my acknowledgement, and I'm going to go into some show and tell of what we're going to be demonstrating later today. And so let's see if I can switch over to here. So, okay. So one of the things that we're doing today is showing off running the MATLAB and Xilinx Toolflow inside of a Jupyter hub. And this is extremely fresh. It's only been working for a couple of days. We've had other types of containerized remote desktop, no GL, no VNC wrappered containers, but integrating it into the Jupyter Lab hub made it infinitely easy for me. So right now I'm in the admin view and I can see all of the different servers that have been started and are running. And you can see I can access the server because I'm an admin. There's 2 admins in this particular instance. And if I wanted to start my other server for the other me, I just click on this and it gives me a list of different containers that I can fire off. And I'm just going to use the Casper one that we customized. While that's firing up, you notice it couldn't find a node all of a sudden, but it's going to go find some node that it can push an OSG or a ice cube job off of. So we'll come back to that in a second. Here's my instance running. So right now I've got a whole bunch of desktops running. And these are all the users, and I'm just viewing their desktop. This is Jonathan's. He set something up and actually ran it. So he can explain what he's got running in there. But here you can see I've got my my license server is also running in the same namespace. So I have 25 seats available. And we have, this is, because of the dependencies, this is older Vivado and MATLAB code. And so we had to build a custom container with Ubuntu 1804 LTS and KDE, otherwise it wouldn't have worked. But that only took maybe a day to pick through the issues and to get it spun up. And once that's happening, we added things like GNU Radio in 2 minutes. So, once you've got this running, if you just make this full screen, right now there's a couple of issues about cut and paste not working, but it's just the little HTML wrapper for no VNC is just this dumb one that doesn't do that. we can easily extend that. But yeah, you've got a full desktop available to do anything you care to. Let's see. Let's come. Oops, I was in the wrong window here. Another full screen. Jonathan, did you want to describe what you have running here? Maybe
yeah,
show
sure.
off how you can simultaneously operate in this screen.
Yeah. So, this was all just very simple, just to show people that it could work. So, I created, I started with my directory. I created a little Casper subdirectory, downloaded the Toolflow with Git. The branch that you want is the M2019A, because we were running Ubuntu 18, and I thought we might as well go with the 2019 version of the Toolflow. So we've got MATLAB 2019. There's a little cloud local startSG that sort of has the right paths built into it for Vivado and MATLAB, and you can start that up. And then I just put together a very simple counter and simulated to make sure that that would work and do what you expect. And also earlier, which I won't go through now, I took the spectrometer tutorial and updated it to 2019 and compiled 2019 MATLAB and compiled that and compiled fine to run. So just as a sort of general example of what we've got, though I can see, oh yeah, my vocals got a little bit out of sync with the video, I noticed there. Takes a little bit of time to percolate.
John and John, I'm going to have to ask you to wrap up quickly.
Yep.
But there is, of course, the tutorial at 1900 GMT, which will take this conversation further.
Yeah, that's about it. Just wanted to show off what will be coming. So if there's questions, I can either answer them now or online.
Fantastic. I think in the interest of time, let's go to the next speaker, but there will probably be some questions in the chat. And then again, later on during the tutorial, there'll be opportunity to discuss. So thank you very much. That's all very interesting stuff.
My pleasure.
Our next speaker is Bela Dixit from the GMRT. Speaking about the resource optimized FBA Beamformer prototype based on Casper tools. So Bela, if you want to get started up.
Yeah, thank you.
Okay,
hello.
Good to go.
Good morning. Yeah, thanks. Hello. Good morning, good afternoon, and good evening to all. I'm Bela from GMRT NCRA Pune. I would like to present our work on behalf of our team entitled Resource Optimized FPGA Beamformer Prototype using Casper Toolflow for Expanded GMRT. Expanded GMRT has three important features. First one is add antenna on shorter baseline, which improving overall sensitivity. Second is add antenna on longer baseline, which improve the angular resolution and confusion limit. And third one is replace single pixel field by the focal plane array to improve the field of view and sky survey speed. Today's presentation is focused on a third feature. Expanded GMRT planned eGMRT beamformer for 550 to 850 dual polarized array. It would be possible to form 30 independent beams, 300 megahertz bandwidth, and 16K spectral channels. Now we look at the free space test range. This is L-band 8x9 WLD feed used for prototype testing. Now look at the figure at the top. This is the 3-meter radiator at the cross dipole at the prime focus. This is this focal plane array is placed in its far field. Optical fiber-based transport used to carry signal from FPGA to down conversion unit. This is the down conversion unit, converts the RF signal to the baseband signal for the further digitization. Come to the narrow beam beamformer signal flow part. This is a baseband signal digitized using 64 channel 12-bit ADC at 64 MSPS sampling rate. Baseband signal is after digitization, it is a time division multiplexing pattern. This 4 signal on one lane. Vertex 5 based Roach1 board used to process for digitized data. This correlator and beamformer output recorded on acquisition PC through 1 GB port, and raw voltage data is recorded through a 10 GB port. Here we see the FP beamformer prototype implementation part. This prototype is implemented for 32 input, 5 beam, 1K spectral channel and 32 MHz bandwidth on a single Roach1 board. See the figure at the top. This is a correlator part of the design. 32 digitized time domain signal is converted to frequency domain using FFT algorithm. Correlator and MAC used to compute complex weights for beamforming. Obtained weights are applied to the beamformer. Because of complex nature of the weights, beam steering and beam shaping is possible. And now come to the resource optimization part. To process 32 input on a single Roach board is not possible because of design optimization using 2 strategies. Here is the first one. Correlator part of the design is optimized for row-wise computation of correlation matrix using the multiplexer approach by changing the reference elements. Here is some correlation matrix. This is the magnitude part and the phase part. By changing this taking reference element as a A4, we compute this whole row. After, by changing reference element by A4 to V4, and simultaneously means similarly for C, D and other. And second one is a separate design for correlator and beamformer. Beamformer and correlator implemented on time shared basis, as correlator information is required only at a distinct interval to compute the weights. Compared to the simultaneous implementation of correlation and beamformer, this scheme reduces the resource optimization by 50%. In this bar chart, this first one is a simultaneous correlator and beamformer approach, whereas the middle one is a separate, only a beamformer part of the design. Here you can see the first one utilizes approximately 78% resources, while single beam design uses only 44% resources. So this is 50% resources became free. Because of this, it is possible to accommodate more number of elements. Here we can accommodate 32 inputs and more number of beam from 4 to 5 on a single vertex 5 FPGA. Beam steering, here we tested beam steering part. Beam steering part of design is tested using the free space test range, as I shown for second slide. This phased array beam tested with noise radiation and a satellite signal. In the radiated signal part, FP8 element linear array beam steer across the radiator, and the theoretical beam width is 15 degree, where the obtained beam width is 17 degree. This observed small differences because of negligence of mutual coupling effect in a phased array beam. Now come to the next testing, satellite signal observation part. IRNSS-C satellite signal is observed by forming the beam at 83 degree east. To optimal beam forming, prototype is being tested with max SNR algorithm. This algorithm optimal weights are calculated using the on-source and off-source covariance matrices. In this case, on-source is radiation off, and on-source is radiation on. Let's concentrate on effect of mutual coupling on beamforming performance. In this context, there are 2 cases. First is related to less coupling between the elements. At left side plot, the mutual coupling values varies from 3% to 10% along the diagonal. You can see here. The SNR values are nearly same for the phased array and the optimal beams. In the second case, however, you can see the diagonal the values, mutual coupling values along the diagonal are 5% to 16%. And right side plot, you can see this SNR performance in a SNR beamformer is higher than the coherent beam or a phased array beam. In this slide, effect of number on element on SNR investigated. In a coherent beam, SNR difference between the 4 and 8 element is approximately 2 dB, while in a optimal beam it is 3 dB. Expected results are obtained with a max SNR algorithm because it takes care of mutual coupling effect. Actual hardware is capable to form simultaneous 5 beams, where here we tested 2 simultaneous beam with a 8 element linear array by radiating tone signal. This is beam 1 is with phased array beam, and a beam 2 is a optimal beam with a max SNR. Here also you can see the max SNR beam or optimal beam performance is better than the coherent beam. We are exploring RF-SoC based ZSU111 platform to build wideband beamformer. RF-SoC eliminates the use of bulky DCU unit using in an existing system. We did some basic testing with a RF-SoC board by replacing DCU, ADC and digital processing board by using the Xilinx RF data converter tool. Recorded data is processed offline. Here are some
10 minutes.
Thanks. Here are some results. Left side plot is a 0 to 2 GHz full spectrum, whereas the right side plot is a offline beamformer part. This is, you can see, 900 MHz to 1400 MHz. It's a radiated signal, radiated broadband noise. You can see this band set. And finally, I would like to thank Sudhir Fakatkar, Atul Garame, Hariharan, Narendranath, Jayanta Roy, Nissin Kanekar, Yashwant Gupta, and I would like to thank GMRT Group, Casper Group, and Astron Group. Thank you. Thank you very much.
Thank you, Bela. So let's move straight to questions. And from Hari, there's a question. By how much does the max SNR beamforming reduce the mutual coupling compared to the coherent beamforming?
Hello?
Bela, did you hear the question?
Yeah. Actually, we right now we are tested with 8 elements. So we observed the SNR performance. So this is nearly 2 dB improvement we observed in SNR performance.
Okay,
so,
2 dB improvement in SNR performance.
Yeah.
Okay, thank you. Next question, how are the weights computed? Is the logic implemented in the FPGAs, or are the weights communicated from an external server?
Actually, weights computation is offline using some MATLAB coding, but we computed this on-source and off-source covariance matrices online beam for correlator part.
Okay, thank you.
Yeah.
Any other questions? We have a minute or so. Otherwise, I think we should all thank Bela, because it must be very late where you are.
Thank you. Thank you again.
Thank you, Bela. So this has been a varied session, but there is a little mini theme here. So we're staying with beamformers and moving to Andrew Martens from the South African Radio Astronomy Observatory to talk about the MeerKAT Beamformer. Andrew, if you'd like to get your sharing started up.
Sure, let me just get this. Wait. It says my browser's preventing access. Sorry about this. It worked earlier.
We have a minute or so to spare. While you're trying, let me just remind everyone that there's also the Slack channel to further discussions. If you did not have a chance or if your question didn't get asked, please feel free to take the conversation further in the Slack. And fire away any questions in the chat while the speaker is online. Maybe check on the rest of the program. So after this, we'll have a break, and then there'll be the Toolflow discussion, followed by the PRP tutorial, the Casper on PRP tutorial. So I think there's still a lot to come. Andrew, if all else fails, you can share your presentation with one of us, and we can maybe display it on your behalf. Andrew, do you like to maybe email your presentation or share your presentation with me? I can run it from here. Try to at least. Andrew, are you there? Okay, everyone, apologies for the slight delay while Andrew's sorting out his little glitch. Are there any announcements, Kathryn or anyone else?
No announcements. We could start the break now and then do the presentation after the break instead of, because this was the last presentation before a break, I think.
Yeah, okay, let's just, I think he's dropped off the call and he's going to try to reconnect, if I'm judging by what's happening here. So let's maybe give it 30 seconds or so. There we go, Andrew's back. Andrew's, we're not hearing you, Andrew. You're not muted, but I can't hear you.
Sorry, is this working?
This is better. Yes. Okay. Click over to the presentation, and there we go. Okay.
Okay.
All
Sorry
right.
about that.
Over to you.
Hi. So I'm Andrew. I'm from Soraya, and I'm going to walk you through some of the Beamformer work I've been doing the last, well, couple of years now for MeerKAT. So our group is moving quite quickly over to GPUs. And this might be the last little bit of FPGA work we actually do beyond sort of just maintenance and sort of operation stuff. So to give some context, so we run a standard sort of Casper FX correlator. So there are digitizers on the dishes that stream data back to a central processing room, where each dish is processed by one F engine in an FPGA, and then channelization occurs in the F engines, and a portion of those channels from all F engines is sent to different X engines. So each X engine for correlation and B engine for Beamformer processes a portion of those channels, the same portion from each F engine. The important thing here is that delay compensation is performed in the F engine to align all that data. So the Beamformer work I did assumes that the data arrives sort of bore site aligned. Yeah. And then within the X, so within one of those blocks on the far right there, the XB engines, those are in FPGAs as well. And this is kind of what the internals look like. So speed data enters there on the left and through a 40 gig network block. We do some unpacking and some speed unpacking. We use speed data with our networks, and we have a very deep data buffer implemented in HMC memory to absorb various delays, including sort of actual transmission delays from far antennas and things like that. So we can align all the data in time before further processing, so that it's all properly aligned without any gaps, hopefully. Then we have multiple X engines and B engines in each FPGA, processing each of them processing a different portion of those channels. And we have a small shallow packet buffer which does some final alignment of the data into time, antenna, channel order. So basically, the X engines and the B engines assume that data arrives, first data packet for channel 0 from antenna 0. Then the first data packet from channel 0 from antenna 1, and so on. And the X engines will cross-correlate all those data packets from basically the same time and the same channel, accumulate the results and send it on for further accumulation. And the B engines will combine those packets from the different antennas into a single output. And then finally, so in MeerKAT we have 8, well, you could say 4 with 4 beams per polarization being formed. So out of every X engine we have 1 data stream, and out of every B engine we have 8 data streams. So that makes 9 data streams per so per one of those pairs, so we have 36 data streams that we then we need to stream out via the 40 gig network again. So we have a big bus arbiter which shares the bus amongst all of those and tries to make sure that nothing overflows and we don't lose any data. So the B engine internals, which is what I've been working on, are reasonably simple. So data enters on the left there. There's some duplication to basically form the 4 beams per polarization. So each polarization's data is duplicated sort of 4 times. Then we do beam steering, which has been the work I've been doing in the last 6 months or so. What this does is this points each beam at a slightly different place. So they come in after duplication, they're all still pointing at the same place, which is sort of bore sight normally. And then at this point, we steer them at a slightly different point of the sky. And this is done via sort of a phase slope emulating what a delay would do being applied across the band. We then have antenna weighting, which allows us for each antenna in every beam, we can weight the antenna data differently to influence like how the beam, how the beam forms and stuff. Finally, the data is all combined. So all the antennas up to 64, we have 64 antennas in MeerKAT, data is combined into a single output. And then finally, we requantize. So in those previous stages, we grow the data so that we don't lose some signal and some of the so we basically requantize to get it back down to 8 bits. So data enters on the left in 8-bit complex value, and it exits again as an 8-bit complex value on the other side. Okay, and then the work that I've been doing over the last year is to create the beam steerer, do the beam steering. And basically, in this image, if you look at this is like a little simple 4 antenna example, but we want to implement a phase slope for each antenna in this beam. And you can see the phase slope that we want to implement, or the delay that we want to implement with the phase slope can be seen. So each one has a slightly different phase slope, and that phase slope for every channel has a slightly different, there's a slightly different complex number, which equates to a phase slope for each channel. So the way I do this is that I have an initial, if you look at each of those phase slopes, there's sort of an initial phase at channel 0, and then there's a sort of phase change for each channel, which is linear. So an easy way to do this is literally just to have that initial phase at channel 0, get rid out of a buffer as channel 0's data comes in. We apply that value to that sort of data, and then we update that phase value for the next channel. So we rotate that phasor by the increment amount, and we write it back to a buffer. What would actually happen is the block for antenna 0 would come through for channel 0 would come through for antenna 0, then channel 0 for antenna 1, then channel 0 for antenna 2, and so on. So each of those values would change, would be different and would be updated. And then as channel 1 comes through that phase storage buffer, the value would get read out, get applied, and then get updated again and written back. So we're taking advantage of the fact that these phase slopes are linear, so that we can approximate them by just updating this phase value in a sort of linear fashion, instead of having what we could have done is done a big lookup table. But this is sort of this is smaller in terms of resources. So what must be noted is we're not actually delaying the data. So this is the same as what James went over for fine delay yesterday. Is we're literally just rotating the phase as though to the same phase as though we had applied a delay. Yeah. So basically this thing was implemented in a way to reduce BRAM with 8 beams and 4 B engines on each FPGA. You can quickly run into very large BRAM requirements. So this sort of update, this sort of feedback update method uses a lot less storage for sort of small numbers of beams. It might change for large numbers of beams. Software determines that delay slope. So basically, we get a message from our signal processing team that tells us what delay we need to apply to which beam, to which antenna on which beam. We calculate that initial phase and the update for each X engine on every scarab, and then we write those values in, and then it runs that until a new update comes.
Andrew,
so it's kind of cool. So it's kind of like a beam pointing. It doesn't dynamically update within the FPGA. And then the current status is we currently have a single beam per polarization without beam steering deployed. And the idea is to deploy this 4 beam per polarization with beam steering, like as soon as we've done testing. We're busy in testing now. Yeah. Okay, and that's it. So that's me. If anyone wants to get hold of me, I can. Yeah, the block. It's not in the library at the moment, but if you're interested in getting it or learning about it, let me know.
Great, thanks, Andrew. So we are in the break time now. So those of you who want to take a break, feel free to do so. We got pretty close to on time, only a few technical glitches that maybe got us over the time a bit. But I am going to just go through the questions. So please feel free to break. But Andrew, there are 2 questions. How stable are the antenna weights, and how often do you have to estimate them?
I'm not sure. So these weights, I'm not actually sure. We provide the hooks. I'm not sure how in anger this beamformer has been used. As like the default is we just have one applied to everything. But I'm not sure actually what the scientists have like how they've actually used these, how these weights, yeah, what they use them for.
How quickly can you update them?
Our aim is to be of the weights. So the weights are quite small. The delays are a separate thing. So the weights can be updated separately, if that makes sense. They're seen as 2 separate things in our thing, but we're aiming at for the delay model. I think it's supposed to be once every second that we update these things.
Okay, and the weights could be the same.
Yeah, I think the weights can actually be done a bit quicker. There's less actual data involved.
Less of it. Okay.
Actually,
all right.
sorry, it's Alec, right? Alec Rusty, the weights take a bit longer because they get updated per scarab and it takes a while.
Okay.
Yeah.
Yeah, Alec does more of the operation side, so he actually knows how they use this thing.
Okay. Then Alec might be interested in the next question too. So how far from bore site can you steer beams using phase slope corrections only on longer baselines at the various bands of MeerKAT? And then it was corrected to say phase slope only weights.
So that's an interesting question because as I said, we're kind of cheating. We're not actually delaying these things. So you're going to get decorrelation as you try to steer further out by applying larger delays. I'm not exactly sure what the requirement is. The system engineering people did some work, and they seem quite happy with like I think it was a 10 or 20 degree error on that phase on the phase for that. So I think they're quite confident that that we can steer to where we need to be without doing it properly. But I'm not sure where they're aiming, how far they're actually aiming from bore site.
So you might be able to test this and write it up in a nice paper.
Yeah, that would be, yeah.
Okay, thanks. I think that's it for now. I'll let you go. Thank you, Andrew, and thanks to all the speakers. So we have about 11 minutes left of our break, and then we'll start the Toolflow discussion at 1600 or 1800 GMT. Thank you, everyone.
All right, should we get started with the Toolflow discussion?
Yeah, I think so.
All right, thank you. Thank you so much. Thanks for attending the Toolflow discussion. We will deliberate on various aspects of the Toolflow. So I will share a screen here. See where the options. Okay. Let's minimize these things here. And then I'll open a new Google Doc. Okay, so we'll start off the discussion now. I have preliminary items that I can populate on this Google Sheet we can talk about, and then we can add on to whatever we want to talk about. So what I have from my side is, let's start there, Toolflow discussion. Then we can touch on get that. So there is need probably to talk about support of the Casper Toolflow, and maybe specifically Ubuntu 16.04 LTS versus updated Python packages.
I think maybe the Jasper Toolflow thought would be nice.
Sorry?
I think there was something called the Jasper Toolflow. Maybe some updates on that would be nice. I don't know if anyone here is actually working on that.
Right, so I've just put it like that if you're happy with that.
Mathews, if you want to share this document, I'll help you edit it as we go.
Okay, can I share it with you? Okay, so that's interesting. Sorry.
That's the name of the document.
Yeah, okay, so must share with Wes. Okay, there you go. Which one? This is the first one, yeah.
Yeah, that's the right one. Thanks.
All right, so that's that, and maybe let's do that. Let's talk about support for Ubuntu 04, support for 1804. Do you want to write that?
Mathews?
Yes.
The text on your screen isn't really readable. So
is it not readable?
Okay, yeah, so I'll share it from my side if that'll help.
Okay, all right.
And also someone pointed out in the chat that it might be that the screen share is optimized for video. And if you undo that, it might share it higher.
Okay, maybe let me start it off again. So let's, and then I must, does that look better now? Or not?
Much better. Oh, that's much better. Yeah. Okay, that's fine.
So 1804 LTS. And so one more thing, Casper FPGA. Casper FPGA.
While you're typing there, Mathews, is there anything else that anyone else wants to put on the agenda?
Yeah, there is one more thing. So there is talk about RVO or Vitus into integration into the Toolflow. And that will be, are you going for that before I start typing?
Go for it.
Okay, so that's OVRO Vitus, integrating that into the Toolflow. Just last thing is that's the PRP from my side. So you can add on something that we need to talk about here. So I don't know if anyone wants us to talk about something specific.
Mathews, what I'd like to do is with the Alveo, make it a more generic thing. Just want to know if anyone is interested in supporting Vitus for the Toolflow. If anyone is using Vitus and would like to see it incorporated into the Casper flow.
All right.
And Matt, and sorry, this is Mitch Burnett. Hey, Wes.
Hey, Mitch.
And so I know I keep harping on this, and I feel like whenever we say incorporating Vitus in the Toolflow, I think we should talk about to what extent we want to incorporate Vitus. What are the use cases people particularly want to target?
Okay. Come on. Mathews?
All right. Okay. So,
sorry, Mathews, what is PRP?
That's
Specific research platform. It's Casper in the cloud.
Okay, great.
All right. Okay, what else do we want to talk about? If anyone put something burning.
Cool. Let's take it away.
Sorry, Mathews. I did mention in the chat, but if I can just discuss the Casper DSP Toolflow.
I got it.
Casper. Are you going for it? Oh, all right. Quick.
Hey, this is Robert Anderson. I'll just real quick regarding Vitus Toolflow support. I'm checking internally right now to find out what MathWorks' current plan is. Sounds like there's definitely some interest with Model Composer integration, but I just need to get the sort of the official messaging on that.
Yeah, great. It'll be useful to have a discussion, possibly post this to actually. And we've actually started some chat with MathWorks, on our side from South Africa through our distributor Optimum. In fact, just yesterday. So it'll be interesting if you can provide any more answers. They didn't have a lot of answers for us, but we both needed to go away and do a bit more research before coming back to the table. So please excuse the kids in the background.
No worries. Yeah, definitely. You'll get another voice from me as well internally. So maybe we can add a little coherence, so to speak, to that message.
But anything else? If not,
is Vitus more or less the HLS high-level synthesis?
Hey, Dave. So that's one of the things that I want to target because, so again, I may be resounding things I've said before. Vitus is a loaded term. And I just want to be clear with what everybody means because depending on the circles that you're talking to, saying integrated with Vitus could be HLS or integrated with Vitus could just mean building out your own custom software C application to run on the embedded processor. And so Vitis more or less is just an added additional part of the Toolflow that incorporates the embedded processor, and then tacked onto it is the ability to use the processor as an accelerator using things like OpenCL and HLS. So yes, it is HLS, but I think we need to differentiate. That's what I meant by what are the use cases people interested in? Do we want to support Vitis to the support that users can add their own OpenCL block that then will wrap up into the Toolflow somehow, which can be done. It's just it looks a little different than just say supporting it as a software platform that we then just build, say, TCP Borf server and let people hook in their own custom executables in. So
we're interested in it out on the Pacific Research platform because it gives our users easy access via PyTorch, Caffe, and TensorFlow.
Yeah, so you're interested in the accelerator aspect,
among other reasons.
Okay.
It seems like system on chip integration is also something that we need to think about more these days.
And that's exactly right. And that was the essence of what I believe to be the foundation for bringing all of the other accelerator works into the platform. If we focus more on the system on chip architecture, then we can make use of the similar tools that, say, Vitis is using to kind of build out and match with Vitis's implementation. Because under the hood, Vitis is using nothing more than some open source tools called hardware software interface, and then some custom scripts that Xilinx uses. And so if we focus on the system on chip, building out that framework, we'll then be able to add in these ideas of using it as an accelerator, which would just be a block of sorts inside Casper or whatever our flow graph thing is.
Mitch, that's some interesting concepts you're touching on there, and I'd love to spend time fleshing those out. Cool. Okay, so I've shared the document with you, Mitch, if you want to maybe just put some of these ideas down as well, and we can kind of chat about them when we get there. Sorry, okay. Dave, jump in.
The KV260 was also mentioned earlier. We've already purchased 2 of those at UCSD, and SDSU has also purchased 2. They will be integrated into our cluster, so you can basically provision them.
Is it like that? Thank you. KV260. Is it the system on modules?
Yeah, that's the dev kit. The module is the KV26, and they come in multiple environmental ranges. I think -50 to +100 something.
All right. Okay, so is there anything else that we want to talk about before we just dive into the actual discussion? We can add on to the item list as we go on, if you haven't thought about it, but we probably can go into the discussion right away. So the first one there is just coming up because of numerous support requests. Because the updated Python packages are not being supported now in Ubuntu 16.04. So what do people think we do? So as the Python packages are updated, so you get numerous errors as you run the Toolflow in 16.04. It's probably benchmarked or let's say baselined on some specific version of Python.
Yeah, so I think the simplest way is just at the moment we have in the requirements file minimum versions of tools, but we didn't specify specific versions of tools. So we're just updating that to be, you must install this specific version of NumPy and this specific version of whatever, which we know works. But I should point out, leading into point number 2, so the Toolflow works fine on Ubuntu 18.04 so long as you install the KDE full package, because there's something about Ubuntu that requires that. And
Jonathan, sorry, I don't know if that blanket statement is 100% correct, because we haven't had much luck running the tools for Scarab on 18.04.
Oh, interesting. So yeah, I've had no trouble with everything else. So
okay. We haven't upgraded particularly because we're just comfortable with, and it's worked for us. So we didn't see any need to upgrade. We didn't have any issues or bugs that we needed fixed. So we've continued with 16.04, and we probably won't upgrade support for it.
Well, so I should say that I think the main Toolflow is going to move on without you there. So we'll have the branch on the Toolflow for 2018 MATLAB and 2016, and then everything else is going to have to move forward.
So we've tagged it on our side and keep going. So it's cool.
Yeah, I have compiled for Retire on Ubuntu 18, so I'm not sure.
Look, we haven't put a lot of effort in it. I know I've tried it at Cheapers, but that was a little while ago. Morag's also tried it, and she's actually.
I'm running 18.04 at the moment, so it works. But I
for Scarab,
I got it by hooks and crooks to get it working. So I just want to find out if there are any very specific tricks that you need to get it working.
Okay, if you can maybe document those, Mathews, that would be quite helpful.
Yes,
we can have a look at. Great. Okay, so Jonathan, you say everything else is running on 18.04.
Yeah, it seems to be. Once I installed the KDE full as per Jack's instructions on the mailing list when he encountered it about a week before I did. That seems everything's been running smoothly since. I haven't had any issues with it. And that's Python.
What do you call this? Is KDE?
KDE-full.
-4.
Oh,
so you need to install
KDE, so dash FULL.
Sorry.
I'm just curious, do you know why KDE is necessary? Because I've also experienced.
Which packages is this?
There's probably just one package in there that you actually need, but we don't know which one it is. So we install KDE full and it solves the problem.
Okay.
We have it containerized, so we can experiment with putting in just one container at a time and see what it breaks.
Yeah. I should point out that John and I were playing with this the last couple of days, trying to get the Toolflow running on Ubuntu 20, and it had the same errors that you get on Ubuntu 18 before you do the KDE installation. And unfortunately, it did not fix it this time when we installed KDE full. So
I have everything running on Ubuntu 20, and on Ubuntu 20, the problem I had to overcome was that the built-in Ubuntu 20 libgmp does not have all the linked methods needed that Xilinx is looking for in system generator.
Right.
And so if you just bring in, if you either update libgmp or then just kind of squash your libgmp with Vivatos, then everything should work.
Yeah, you might be able to preload their library.
Yeah. That's right. Yep.
Cool. Okay. I'll try that and see. Thanks.
This is probably a task for busy week, but
yeah.
But yeah, I think let's push for 20.04. That sounds promising. Thanks, Mitch.
I already have the Vivado, Vitas, and MATLAB working, the latest versions. But we can downgrade those to run in 20.04 too. So that's all containerized if you want it.
Cool, thanks.
All right. Right, so this also maybe there is documentation to this 16.04, but it doesn't say that you need to specify it. Maybe you need update documentation so that whenever one is installing based on the documentation, then that must be stated.
Yeah, well, the idea is you won't have to. We need to just update the requirements.txt file to specify the specific versions, and then it should be fine.
Oh, okay.
It's
All
just
right,
at
sure.
the moment it only the requirements.txt only has minimum versions specified in for pip, and when Ubuntu went to some Python change recently, that broke a bunch of stuff. So there are specific versions that work. We just need to go in there and tell it to use those specific versions. This is part of the general. These are problems that have been fixed, but we haven't had time to merge back into the main repository.
Yeah, that makes sense.
Yeah.
If you'd like, we could also build a 1604 snapshot for you guys for Scarab.
John, at the moment, I think let's leave it. It seems like it might not be too big a deal to upgrade to 18, so we'll try that on our side this week or next week. And then we
One
can...
nice thing about putting stuff in containers, you can keep old crusty stuff alive for a long time.
Yeah, very much so.
Right, so yeah, let's probably move on to FPGA. Python 3 support. I think there's some effort that was done by Amit or Talon, but it seems like there is more work to be done. So I think the question which Adam was asking was, is it worth that effort?
Yeah, so there's a JAX running entirely Casper FPGA in Python 3, and it works, as far as I can tell, for everything except the onboard calibration of the Snap ADCs. And the Hera branch of Casper FPGA has that fixed, but it uses some Hera custom code, so I need to strip that out and merge it back in, and then we should be able to move entirely to Python 3 Casper FPGA.
There's a few issues that I saw with Casper 3. So, like, for example, the snapshot block. In Python 3, they got rid of, I'm having to remember by recreating the bug, but essentially they got rid of the lower level int types. And so there was a lot of casting in, say, if you did a snapshot to, if you had a short to an int8 or whatever, it's just all an int now in Python 3. So I had to go in and change some of those around on my Python 3. I don't know if that's made it back anywhere else.
Was that the Python 3, Mitch, that you grabbed from the Casper Astro?
Yeah, that's right.
Okay,
Yeah,
so
that's right.
JAX PCIe transport layer of Casper FPGA is very, very diverged from that.
So I should have started from there. Okay.
Yeah, so I mean, he may not have fixed this already yet. Maybe you've got the only fix, but I'm actually going to blow away the Py3 merge version and just start from JAX when I merge in the Hera stuff.
Okay. All right, cool.
Jonathan, what platforms have you tested that on?
I've tested it on Ubuntu 18.
Okay, so and hardware platforms, have you?
Oh,
we've got some caveats, particularly on Scarab, where we call.
Yeah, so I've not tested with Scarab.
Okay.
I've tested basic functionality with snaps, apart from the ADC calibration, VCU 118, the VCU 128. Those sort of anything using the TAP-CP protocol I've tested. They tend to be the ones that I've been working with.
Okay, great, thanks. We'll test it on our side.
Which versions of Python 3 has this been done on?
This is 3.7 now. We were using 3.6 for a while and then updated, Ubuntu 18 went 3.7 by default or something, and now we've been using 3.7 and it seems to be working fine.
Because it seems like the concept of a string is still changing or something in Python, and so it's a little bit tricky.
I do have a version of this. I'm rewriting Casper FPGA in Julia, but it's a slow process. And at the moment, it just imports all of Casper FPGA via a Python wrapper and runs it that way. Yeah.
Okay.
Is there a Conda version of Casper FPGA, or will there be a sort of packaged release on Conda Forge or something like that? Or could we put that on the to-do list roadmap?
I think it was supposed to be put onto pip.
Yeah, there is a pip version. It's the 2.7 version, and that is currently how you install it. If you're using the standard Python 2.7, you just do the pip install the requirements and then pip install Casper FPGA, and that does it.
Conda seems to have better like dependency management than pip, for what that's worth.
I don't care that much, but whatever we go with, I want to move everything because I really don't want to end up managing multiple. So if the requirements, at the moment we just do pip install requirements.txt, whatever. However we set it all up with Conda or whatever, that's fine, but let's pick one and go with it.
Jonathan, can I ask that you look at our branch of Casper FPGA, because I know that has moved on a little bit.
Yep.
I can issue a pull request as well.
Yep.
And then once you're happy with the 3.7 port, just let us know and we can test it on Scarab.
Sure. Yep.
Thanks.
Okay, and the documentation for installing hardware FPGA in Python 3.7, is it the same as Python 2.7 or?
Yeah, the docs are currently set for Python 2.7. So when we move to Python 3 as the main version, we'll have to update the docs.
Yeah. Okay.
I have
anything
comment,
else
I
on
guess,
Casper
about-
FPGA?
I have a question
ahead.
or comment, I guess, about Casper FPGA on SoC type systems. It seems like there's a lot of different kinds of integration with the sort of CPU that the gateware can have. And I'm wondering if Casper FPGA needs to be sort of adapted to support that, if there are plans for that, or if anybody's done any work on that already.
I can comment a little bit, but
there we go, Mitch, go ahead.
So as far as SoCs, I guess correct me if I'm wrong, I don't know. The only SoCs we would have in the Toolflow are the Repetaya, which is a Zinc 7 series, and then the ZC111 and everything else I've been doing. In my opinion, I like TCP Borg server. It may be old, but it does everything we need to do. And what I wasn't able to share I could have given a whole other talk based on what I did to help support SOC through Casper FPGA, is that I'm just using the same old CAT-CP transport to communicate with CAT-CP and implementing all the SOC specific things inside TCP Borg server. And inside Borg server, there's this ability for modes for the FPGA to take different form based on what it looks like. And I haven't yet used the full API or everything in Borg server to do that, but I've kind of segmented it to be that way. So that way you could move into an MP SOC mode in Borg server if you're developing on a SOC that enables all sorts of SOC options, and then move out of that mode back to the raw mode that would just be a plain old FPGA that has no SOC on it. So for example, in the RF SOC, the big thing is the device tree, applying device tree overlays to key off to the processor which IP is in so the device tree, if you're not familiar with it, is a hardware description for the kernel to know, okay, what am I looking at? And it has a specific section for the AMBA PL. And inside the PL are all of your IP and any sort of hardware handoff specific characteristics that the software would need to know about the IP. For example, what address it lives on the memory map, or in the case of the RF SOC, all of the device driver configuration for what the sample rate is, et cetera, et cetera. And so I've gone in for the SOC, and on the RF SOC, which would work on any, the Zinc 7 or the MP SOC, a device tree overlay inside TCP Borg server. And in that sense, all the way back to your question, Dave, Casper FPGA just works because the CAT-CP transport is already built in. And so now you're just using, we would change Casper FPGA to the extent that we're just extending CAT-CP calls using CAT-CP transport to do that communication.
That sounds awesome.
Mitch, 2 questions. One, when do you sleep?
Well, you have kids, right? So you know never, right? You're up until
Yeah,
12 and
much.
1, and then some kid decides to get up, and then you just keep going. So.
Tell me about it. That's what I'm looking forward to tonight. And then second of all, we're looking at doing something like this with the alveos. So obviously with the host machine running some TCP/BORF server speaking over PCIe to the card. But there's also your host code. So we're looking at some way of kind of integrating that host code that you generate through Vitis with
and there's no
stuff.
and there's no way that PCIe will work exactly inside TCP/BORF server. We just have to extend using Xilinx's UIO kernel libmetal to use the PCIe definitions, and then it just all becomes a libsysfs stuff. If you're familiar with libsysfs of using system. I'm not a huge kernel developer, so I'm probably botching these words in a scary way, but Dave may be able to help. But
Well, this is kind of going full circle back to the original BORF concept.
Exactly, and that's
files.
what it is, and that's what it is. Is we've been here in Casper, we've been doing it for a long time, and now the embedded community is just catching up to what we've been doing. And then, because I was a big proponent of looking into all of these other, but then as I dug deep down, I was like, because I've been a Casper user before I became a real hardcore developer, and then now as I'm developing and I'm comparing with everybody else, I'm like, well, we've already just been doing what everybody else is now doing. So
what we found though is, so with Red Battalion, it was if I'm not mistaken, device drivers. So it was like a file that you could just write to and it automatically read and read registers on your device. With the alveos, it's slightly different, and I don't know the details, but Robin, I see, is on this call, and he's been doing some work on the drivers on the alveo side. Robin, are you at your desk there? Are you able to comment on this?
Hi, everyone.
Hey, Robin.
Yeah, so with the alveo, we will probably make some C API calls through the XRT, the Xilinx runtime that runs on the host. So that's probably slightly different than memory mapping the address space into your process.
Cool, thanks, Robin. Yeah, so we found it wasn't exactly the same on the alveos as it was on the Red Battalions, but
which is so which I granted I'm also not familiar with the alveo as much. I do know about the Xilinx runtime and the Xilinx shell that is the Xilinx runtime. But when I poke around looking at the hardware-software interface that Vitis uses, it does look the Xilinx runtime has a bit of a pseudo API that you can key off and command, and we would just use those. I'm speaking in very vague terms because, like I said, I didn't look at it, but it seemed like the runtime was extendable, just like any other framework runtime, CUDA runtime, or any other runtime framework that you can just program in to key off the runtime and tell the runtime to manage its job. So it would look a lot like a GPU in the sense that you just call runtime device driver things, and then what's running on the alveo, that shell kernel that's interfacing between the two, it would just manage based on what we commanded in TCP/BORF server to set up the runtime, configure the runtime, and then go.
Sure, yeah, that sounds pretty cool. I've got some reading and research to do.
So they've released a FPGA as a service integration for Kubernetes that includes managing the hardware, uploading runtimes to the devices. I think there's 3 or 4 packages in that repo. I'll get it and paste it in the chat.
Yeah, if you could do that, John, that may save me a ton of time so I can come up to speed on it.
All right. Yeah, anything else on that note? I presume we were already talking about on point number 4. Because that's where the Vitis stuff is.
Oh, this is Robert Anderson again. I'll go ahead and share. I was speaking with development. And this is a conservative statement regarding MathWorks. The integration with Vitis will show up in the product officially in 2022B. So, that's a while. And pretty much in line with, MathWorks tends to be quite conservative with stuff like this. What I'm trying to find out, and I'll just throw this out there, if there's some front work, it sounds like you folks have done some pretty good pieces in here that support very high speed. And what I brought up to development just now was if there's a way we could work on something jointly to sort of, grease the skids, if you will, maybe to provide some form of integration between Model Composer and MathWorks a little earlier. I'm not saying it can happen, but I just wanted to bring it up as sort of a, big, a goal, I guess.
Yeah, thanks. I think, as Mitch was saying, we need to really define what our use case is, because at the moment we've used Vitis and system generator with Vivado, and create a project from that, and then pass it off to the Vivado tools. But we kind of need to look at how do we want to use this going forward? What are the use cases, and how do we integrate? What tools are best suited to that, and how do we integrate that into our flow, if at all, or do we create a different flow?
Right.
Mitch, you had some ideas on this. What were you thinking?
So I'm not entirely really familiar with Model Composer, but if I had to guess, the answer, yes, I'm in line with you that which we go with depends on our flow, and how it's presented to the user will depend on what we go with, Model Composer versus System Generator. So if it's a System Generator approach, then it will continue to be the same old Casper philosophy, where we define a new yellow block, a pink yellow block that's pink, and it represents some Vitis component that we then script out to do the whatever Vitis thing we do. If it's Model Composer, where Vitis is going to be coming in, then I imagine it will look just like what we do in the Jasper flow, where under the hood, you insert a bunch of configuration parameters in the Model Composer to key off specific processes, and then Model Composer will go and build out Vitis. And so again, Model Composer, maybe we get for free all of what we would have to implement in Jasper to build out our Vitis use cases. I wish I could comment more, but high level, that's what I can see right now.
Yeah, that makes sense.
Oh, go ahead.
So if you can understand the sort of the details of that interface, that would define how it will look in the larger framework.
What I'm kind of not getting my head around just yet, and I need to kind of probably do some more research, is how, if we want to go with the Vitis flow, your code you write is kind of monolithic, and you kind of just say, okay, implement this part of your code on an FPGA, and then you define the memory interfaces and how the memory transfers work. And then it goes off and pulls in GCC or the Vitis or Vivado compilers. How can we actually overlay that onto the kind of Casper flow, where you've got this kind of yellow block, green block design flow, and then your host code sits outside of that flow, that methodology at the moment. That to me is kind of something I'm not clear about going forward. I need to kind of get my head around.
Yeah, so sorry, Wes, is that a question you would like
it's
to
more just
elaborate on? I can elaborate now a little bit, but I don't want to continue. I mean, if there's other things we want to use the last, I don't know, 20 minutes we have. Otherwise,
I don't think we're going to solve this now. So
yeah,
this is going to be a longer discussion.
The answer to your question is I think I can elaborate for you later. We should just set up times to get together and do it.
Let's do that. If anybody else is interested, just contact myself or Mitch.
Yes, I'll elaborate later. All right, so yeah, maybe just get in contact and have further discussion on this. I don't know what the remaining items, how long they're going to take us. But okay, the next thing is whole device architecture something we are interested in supporting? Any comments on that?
So Mathews, that really is kind of the same.
Yeah, kind of. That's what I was. Yeah, that's what we were asking now, Mathews. Yeah.
D is like
All right,
rewording the entire discussion that we just had. It's like a different way to say what we just asked.
Okay. All right, sure. That's fine. Okay, so maybe now let's talk about the PRP, the Pacific Research Platform. Anybody who has spent time on this and we quickly explain how it works and how we interested as part to get into that.
So anybody that is interested in learning more about the Pacific Research Platform, the Jupyter Lab Hub is available. And if you want to do more scaling, you can just log in to our regular web interface to get Kubernetes access to the cluster. We'll also be integrating on the spawning page for the Jupyter Lab. We'll put a combination of FPGAs and GPUs that you can choose. So when you start your lab notebook, it attaches whatever you ask for. Typically, we're going to be locating a T4 GPU next to every FPGA. NVIDIA did come out with some T1000s that are kind of a laptop game card thing that you can get for $400 or $500 if you could find them in July. So the other thing that we're going to be using is the A10s, which can be, they're single width GPUs, so they'll fit into more devices. And there's a gigabyte chassis that's a 2U chassis that holds 16 of them.
Right, so I think people who are interested may get to the PRP websites and log in, as you said, and possibly get more information about it, and then probably contact the relevant people going forward. All right, anything else on PRP?
So I guess I have a few comments. So I mean, I've only worked with it a little bit on, as far as I know, I think John Koch is the one that's really kind of testing it out and driving it, moving it forward. I mean, I logged in, I wanted to use it, but only on their finite bandwidth, able to poke around. I like and love the idea. I think it's great. I do think we should move this way. But John, so I know Kubernetes, I know a little Kubernetes, I know a little Docker. In the Casper community, do we need to get better at using those tools? So will we need some kind of homebrew knowledge of using Docker, or do you guys support building out these images? Or
we have a pretty extensive support system. We've got a lot of tutorials on how to do a lot of the things you need. The getting started guides in Kubernetes. We also have, half the time we'll just build it for you.
Yeah, okay. Because I mean, from where I sit, I think that's probably the biggest barrier, I think, for A, getting us to use it, and then B, it's kind of a new paradigm where we have to get now into this load balancing and Docker mindset. And that's just a different skill set that I don't think we inside the community have a lot. But I mean, I know there's people doing it. I just don't think inside the core group of folks, we don't have a ton of experience.
This is the place where you can learn all that. As a matter of fact, the skills that we'll teach you are applicable to every cloud because everybody's using Kubernetes. So
that's right.
It's just a really good baseline to start. How do you write a Docker file? Oh my God, they should be teaching that in high school at this point.
I know. Yeah. So yeah. And it's pretty straightforward. It's easy. Yeah. So but for me, like, that's what I'm saying. My endorsement is of it. It's straight. It's easy. It's just skills we need to incorporate. And I'm just saying, I don't think we should be afraid to get down and learn these things. It really will help us.
You can't break anything. That's the other cool thing is, you know, you might break your own thing, but you're not going to break the thing next to you. So we have a lot of pretty radical experiments run in our cluster.
Okay, great. If there's nothing else to talk about the Pacific Research Platform, we may move on to the next item, item 6, as far as DSP development tools.
I suppose I should talk about this, or Jonathan. But basically, this is a very quick thing. I think many of you might be aware of. Well, some of you have used it, but basically, this Casper DSP Toolflow is a separate repository that we'll be collaborating on, possibly with Astron in the future. And so the idea is to have pure HDL in one repository and incorporate it into the Toolflow, which we have been doing. So currently it's set up really neatly in that you clone 2 repositories, one being the HDL and one being obviously mlibdevel. And in the start.sg local, you just specify the path to the HDL, and it should incorporate the HDL cores and their wrappers, their Simulink wrappers, and place it in an HDL library inside Simulink. And so from there, yeah, you're able to drop in blocks and work as usual. So that's basically just what I wanted to mention, is that this Toolflow sort of serves as a plugin of HDL cores into the mlibdevel Toolflow. And I think it works for, well, I know it works for JAX mlibdevel. It's not really a fork, but it's JAX mlibdevel. And later we could try and make it part of the current mlibdevel platform.
Talon, what libraries do you support at the moment? What DSP libraries?
Well, wrapper-wise, like having actual Simulink wrappers, we only have Simulink wrappers for the PFB FIR, the wideband FFT, and the pipeline FFT. But we are in the process, well, we're looking to wrap all the cores from the very base level to the top. So all the adders, the multipliers, the muxes, etc. So at some point we could have a very comprehensive library of cores, and then of course, if there are cores in open cores that people are interested in wrapping, that's fairly simple to do as well.
Neat. And have you guys standardized on interfaces between DSP blocks? So do you have axis interface between them, or is it kind of just custom per block? Whatever the designer felt like.
No, currently they're custom, especially at the lower level where you're just dealing with adders, etc.
No, sure.
But the FFT currently has a streaming interface that Astron makes use of, and I don't think they make use of a Avalon streaming interface, but we do have plans to at some point probably put an axis streaming interface or standardize between Astron and, I mean, between Intel and Xilinx and use Wishbone, and then use adapters for axis and adapters for Avalon, because from Wishbone it's simpler to do adapters to those two. And of course, open cores, most of their cores support Wishbone, so it might be more, but that's not been thought of too much yet.
Okay, yeah, sorry, I think there's 2 things here. There's one, the control of registers, that'll generally be either Wishbone or say an axis for light or something.
Oh, right, yeah. So
streaming, sorry.
Yeah. Streaming wise, we would look, yeah, that's remained open, but yes, so Astron does have Avalon memory mapped interfaces, and we're looking to implement selectively implement axis memory mapped interfaces in the same way they have it for Avalon.
Okay, cool.
Yeah.
Thanks.
Okay, anything else on DSP development? Toolflow? Any comments? We have 10
So
minutes to go.
yeah, just to clarify, Talon, right? You're using the black box to do all of this inside system generator, right?
Yeah, unfortunately.
Yeah. Okay. No, I don't think that's unfortunate. It's just
Yeah,
curious.
I mean,
Thanks.
yeah, it's a little more tedious than we like, but I don't know how Wesley's progress with the RTL core has gone, but I mean, maybe that's also something to discuss if
Well, the
RTL.
only thought I had, and I tossed it back and forth with Jack, is what if instead of messing around with like say the black box, we just also have another, like a block similar, right? It's like a yellow block that represents hardware, and then we just provide a simulation version of the core, so that that way
like we
when
do for in the yellow block, yeah.
Yeah, that's right. And so you have a yellow block, it'll just wrap up the hardware, and then when it implements, it knows how to generate, instantiate, and wrap it up. And then if the user simulates it, it then just runs your cycle and bit level accurate simulation model of the core. And then that way we don't have to mess around with any of Xilinx's or system generators black box stuff.
You
Yeah,
just
that's
described
what
system generator.
Say that again, Dave.
You just described system generator, though. That's what it does.
Well, yeah, exactly. No, exactly. You're right. And that's my, yes, no, exactly. And that's kind of what my thought was, is we just kind of now embed in what system generator does, where Xilinx provides their cycle bit at level simulations, and we, the developers of the HDL core, do the same when we add our DSP blocks.
The work there then relies on the designer making sure that his simulation model and his design actually are accurate.
That's a non-trivial.
Yeah, that is true.
Yes.
And that's kind of work, because I have my oversampled PFB, and that's what I've been doing.
Yeah.
And I spend more time trying to get my simulation correct
accurate
than anything else. I mean, it got there and it's working, but it is non-trivial. And so I guess we're coming down to just juxtaposing the non-trivialness of getting this square peg in a round hole, of getting the black box to work with all of your memory files that you're fighting with Talon, right? Or the simulation of the core.
Yeah, so I mean, it's been a while of fighting to get the black box to work, but now I feel pretty confident, and it seems to work quite well, and I've had to develop a couple of automatic tools to get it to work. So I think future wrapping of cores in black boxes is mostly going to be simpler. As for simulation models, we had thought to do that because I have MATLAB simulation models for the FFT and PFB. Obviously, those are floating points, so they're not bit level accurate. But purely for the Simulink environment, you could simulate and run the MATLAB simulation model, and then yeah. So I don't know. Now that things seem to work with black boxes, it's kind of feels simpler to use that for simulation than to generate simulation models myself or program them myself. But yeah, it's definitely worth exploring.
Okay.
I think that a lot of the simulation that gets done with these sort of FFT blocks and things like this in a larger design is more for the timing of the sync pulses and the framing of the spectrum as they come out. And it's not so much is the FFT producing the right numerical answer at that level.
So well, that's a fair point. So that kind of reduces the complexity a lot.
Yeah, so it's just getting the sync right and the sync to data timing and that sort of thing, and maybe latency issues and stuff like that. It's all that really matters at that level, I think.
Point.
Great points there. We have 5 minutes correct me if I'm wrong. We may probably just touch on the last item in the next 5 minutes. Maybe 260.
So I mentioned that we're purchasing, well, between SDSU and UCSD, we'll have 4 of those available to connect to your Jupyter Lab notebooks.
Okay, how much are these?
Those kits are only $200, but you got to read the fine print. But to get the $50 worth of power supply and cable adapters.
All right. There was a presentation to these devices, right? Introducing these devices at some point yesterday, I think.
I believe Dan mentioned them as a module that they were interested in.
Yeah, I was wondering if anybody else is planning to use not the KV, the prototype board, but the actual module on a board. Is any, because we're probably going to do that. Well, thinking about it anyway.
Yeah, Dan, I think we'll find a use for it. Not sure exactly where, but it's certainly a useful device.
Yeah, I think it really takes away a lot of the headache in building FPGA boards if we can start using those things. And I think I'm not sure how pin for pin compatible, but if we could build a base board with some ADCs on it and just use their boards for all the FPGA and power and clocking, that would be a huge benefit in board design.
Yeah, I agree. We have a Contextual Robotics Institute on campus, and they would just love to have these in their vehicles.
So they're working on an RFSoC and an UltraScale Plus version of these things.
And they also have a long lifetime, and they're available in versions that can withstand high temperatures. So if you have a slightly rugged application, they could be very useful.
And they're cheaper than the chips they put on them.
Again, yeah, same as with the LVO.
If I'm not mistaken, some system on modules for RFSoC already are out there, just not from Xilinx.
Oh. I've seen some of that stuff, but it's a little bit different than a board that it's like a little module, connectorized module that you plug into a backplane or something, right?
Right, and that's what those are, yeah.
Okay.
Yeah.
Those things are quite pricey, but if you have an inexpensive one, we're trying to digitize 480 signals, and if anybody finds a cheap way to do that.
Okay, so yeah, we almost on time. Still have 2 minutes though. Maybe we can wrap up. I don't know if you have any other thoughts. Can we wrap up now?
I guess I have one other comment on the KV260. The ARM platform that's driving that, they ported all the Jupyter Lab notebook stuff. So you can actually run an app on their device to interface with the hardware. But I also confirmed that we can run K3S on it and then federate it to any other cluster. So we can containerize our apps and just send them to these devices, which makes it even cooler to just throw these modules on your system and then toss containers to them to orchestrate all the cores.
Great. Useful information. I think it's almost time up now. I've got 1 minute to go. Otherwise, thanks everybody who has attended. Thanks for your contribution to this discussion. And I think I must hand over back to the organizing committee. Thanks everybody.
Thanks, Mathews. Thanks, guys.
Yeah, thanks.
Thank you.
So I guess it's straight into the tutorial now.
Yes, we can start that right away.
So how many people, let's see, I'm gonna log in and see how many people are signed in here. So it looks like we have 7 people live or that have signed in, but we can do the tutorial just by Zoom screen share for those that don't want to push buttons.
I would appreciate that if it's easy to have somebody share their screen with me.
Yeah, well, Jonathan is the one that knows how to drive this stuff, so I can share my screen and just watch what he's doing in his lab.
Sounds good. Though, I mean, there's only so much tutorial we can give here, in that once you've signed into the lab, and started up the desktop, then you're just running a desktop with the Toolflow. So it becomes a case of sort of what you need to do. So we can sort of step through that, but then I'd encourage people to actually try it out and let us know if they run into any problems or issues, or and we can sort of go from there. But as I said very briefly during John's talk earlier, one clones the Toolflow as you normally would, and then it's a case of checking out the branch that we need, which is this M2019A branch for the cloud version, and the StartSG Cloud Local is preset up for you to run, and then it's the standard StartSG Cloud Local will sort of start up the Toolflow for you. So at that point, you just have the environment running, and everything should be set up and working. And the main point of doing some of this that we've been thinking of for a long time was just to avoid the headaches for people setting up the Toolflow the first time. And it turns out the system is actually quite powerful, and we may want to use it as more than just an introductory system. But sort of that's the starting point. And I think, John could talk more about how we would be able to connect through to actual FPGA connected systems if we hook up a snap to one of the servers at Berkeley, how we'd be able to interact with that as well. But
yeah, we can do 100 gigabit a second or better plumbing between labs anywhere on the end of ESNet or Internet 2 connections, all the way into our distributed cluster. And so we have layer 2 gateway nodes that are in Guam, Hawaii, Miami Ampath, Caltech, and Starlight. And from those points, we can drop down into layer 2 plumbing and pop up pretty much anywhere. So we can stitch together all kinds of strange architectures of remote flow simulations. If you're trying to figure out how to stream directly from the mountain into a remote cluster, we can do experiments like that.
And, yeah, I was just going to, with the rest of this, it's just a case of one could open up the Regidocs tutorial and just start working through the tutorials there. At the moment, you cannot use the precompiled tutorial files or pre-developed tutorial files in the tutorials develop Git because they're still MATLAB 2018A, but you could build a new model based on the same instructions. And once they're there, it's simply a run Jasper, like with this tutorial here. We could do that, but then of course we'd lose the system for now. One could literally just, I ran this yesterday, we ran Jasper on it, and it compiled fine.
Actually, let's switch over to, you have the link for the admin interface?
Yeah.
Why don't you drop into a different desktop, and I'll do the same. And I've already staged, let's see, you can, yeah, mine is running, so you can just drop into the JJ-Gram at UCSD.
Okay. Yeah.
And then just fire it off from here.
And did I put the right JJ-Gram? You see the axis, so over there.
So he's just going into the Jupyter interface as the admin, and he's going to drop into this other instance that is running. And I've already fired up MATLAB, so it doesn't take so long to load. Currently, we're using a distributed Ceph file system. The MATLAB and the Xilinx software are on CephFS, remote distributed shared volumes. So every single container has sharing the same software. And it's basically an environment variable in the container that points to the license server on campus for MATLAB and the license server in the namespace for Xilinx. And that the flexibility of having the license server in the namespace for the Xilinx tools means we can run it on any node because we have a coherent namespace across the entire planet. And we're just using the short name. So it's port number at short name, and it finds the license server because it's on the local subnet.
Just while we wait for this one to open, I'll point out that it takes a little bit of time to open up MATLAB or open the model, but the actual compile and other dev is reasonably speedy.
Here it goes. Yeah, the file system isn't the fastest. MATLAB, I think it's like over 1 million files, and on CephFS remote mount, when you fire it up, it gets a little squirrely. So rook block mount for this would be 1,000 times faster.
So just to demonstrate, we're going to get some warnings and complaints, but all of them are ignorable.
So this is in home Jovian. Does this get shared across all users of this kind of system?
No, this is a local copy. It's cloned into the user's persistent volume, home Jovian. So every time the instance spins up a new user, they create a persistent volume for that user. So all their work is there when they come back.
But they see it mounted as home Jovian all the time, I guess, but it's their own.
Yeah, we can change the name. It's just what they.
That's fine, and it's persistent, I guess.
Yeah, and you can attach as many persistent volumes as you want to this. So I have one for MATLAB and another for Xilinx, but you could also have a petabyte storage array just lopped right in there too. We can mount BGFS, Rook. We have our own S3 if you're into objects. Seaweed FS, which is really high performance, all NVMe, only in California right now. And that's good for millions of tiny little files, like for genomics or.
And one other thing I like about, as John was saying, being able to drop into other sessions does mean that debugging could become much easier if somebody's trying to learn how to do a tutorial.
Yes, from anywhere on the planet.
Yeah.
Plus, we can geolocate based on, hey, if I'm coming from Korea, I want to pick the node in Korea so I don't have latency. And then it would use the storage in the Pacific pool and tie it up with a GPU and an FPGA. And then you have a low latency remote workstation.
Can users share their sessions with other users, or can only admins drop into other sessions?
I think with authentication, you can hand them a token. That's right. So the user can produce a token and give it to somebody else to give them access. And we could change that too. It's all using CI logon, which is great. Federated identity. It maintains the ability to have coherent work groups across multiple universities and government labs and businesses even. CI Logon supports anything with a Google managed domain. EduCause, all kinds of different services are kind of aggregated by the CI Logon. And we just use that in our, when you log into our portal, you get a token that's basically your password. And you store that in your .kube folder, and then whenever you type kube control get nodes, it uses that credential to access the cluster, and it recognizes your roles in the cluster and only lets you do things that you are allowed. And so it's all role-based and namespace-based and highly automated, because there's only two of us running this whole mess.
So I should point out that error we got is a known error, and it's been fixed everywhere except the primary emlet for the latest Python. And I fixed it in my local download, but I haven't pushed it back to the main repo yet, which is why that's come up. So
we can switch back to your screen for the.
Sure, let's do that. I'll close this one down. I'll just compile the other one. But yeah, that's a it's on the mailing list. It's been identified. It was Adam Isaacson who found it and pointed it out. It's a issue with just a changing version for PyYAML and how the loader is declared. So yeah, I have to push that back to we have to get that back into the main repository.
The nice thing about containerizing things is it allows you, it's embedded documentation of what you're doing, and it allows you to iterate really quickly. I don't think I've typed make in 6 years. I've just, git push. Make is automatic.
So just to check out that, has anyone logged in and tried to run anything or build anything or had any success or failures?
Let's take a look. Let's see, that was the one we were playing in. Not there, not there. Ah, somebody's working along here. Yes. And no, so yeah, we have one user and the rest are just lurking.
And I think you also have a question in the chat from someone who's trying to connect.
Oh. Let me find the chat. Oh, that's the wrong place to look. I've hidden all the controls. I have no idea where they're at. Let's see. This? No.
I can just read the question.
That'd be easier.
Someone says that they're just trying to connect using the system VNC viewer and wants to know if that's possible. So I think they're having trouble connecting over VNC.
Oh, connecting to the container using VNC? I'm not sure what they're asking. Let's see.
Yes, that was the question, I believe. Clarification on chat was yes, try to connect to the container using VNC viewer.
So you probably could, because it's in the cluster, you'd have to port forward using kube control, port dash forward, the namespace, and then the pod name. And then you could forward to your local laptop the VNC session. And then you could just connect VNC to localhost and it would work, strangely enough. But you can forward any port that's running inside your container right to your laptop. So if you don't want to spin up a whole Jupyter hub, you can just spin up a Jupyter notebook and have its web interface on your 127.0.0.1 localhost. Or you can just define an ingress for that, and we have wildcard DNS and wildcard certs, and yeah, so that tight VNC, that's not going to work because that's going to a load balancer IP address for a service, not the actual container IP. I see in the chat they're asking about an IP address. So yeah, there's a whole bunch of layers. We're in an overlay network in Kubernetes. So we have the physical hosts have their real IPv4 routed network. But on top of that, each host, when they join Kubernetes, we're using Calico as the overlay network. And this allows us to do a 10.224 CIDR for each host. And so each host has got a giant block of private address space that they deal out to containers physically appearing on their side. And then if they're in the same namespace, those same IP addresses for the containers will be visible on any other host in the cluster that's in the same namespace. And so you'll be able to see across the cluster as if there is just on the same switch. And in fact, there could be 20 hops between those two nodes that are running those two containers.
So if you only have one person logged in and working on a tutorial now, do you think maybe you'd want to walk through the steps for logging on? Because I wonder if there are other people who are trying to log on to the tutorial.
Yeah, so that's, I can do that right here. We'll just find one that's not busy, hide these silly controls again. There we go. Oh, I'm going to have to do this as an anonymous, otherwise it thinks I'm logged in. All right, so you basically, you appear and it has this login button for CI logon. Google is the de facto one, but it has, a lot of places included all around the planet. So you can get into it through your local single sign-on. And so if you don't have, find yourself in that list, then you can drop in there. And actually, I should have done this as some other me. Let me try this again here. I have.
And could you drop the link that you want people to go to in the chat?
Yeah, so that's if you check out the Slack 2 on the PRP Cloud channel and on the workshop one, all the instructions are there.
Yeah.
Okay, sorry, maybe this isn't needed then. I just wondered if it would help more people get logged on.
Possibly, if I can find the chat window again. Let's just.
I'll toss it in there.
Okay, thanks. I'm going to continue with my other me. Google, and it says me. And we can customize multiple different containers. So like if you have a Scarab, special Ubuntu 16, you can put that right there as one of these choices. We only have one right now that's sensible for us. And it fires it up. And if I pull up over here, this is K9S. It's a little TUI GUI that shows all the stuff that's running in the namespace. This is a really handy little tool that we use. It's basically kube control command line with a little wrapper around it. So here you can see I'm starting up on Suncave 9. I don't think it's ever run on Suncave 9, so it might take up to a couple of minutes for that to fire off. But I've noticed once we're using a thing called Kraken, which is a Docker container accelerator. It caches commonly used containers in NVMe on all the nodes. So anytime another container asks for it, it streams from all the nodes. And so we get it took 30 seconds to start the last one that had already run on Suncave 10 when I restarted it this morning. And so otherwise it takes a little bit of time to fire that up. And it will tell you if it fails. And actually, we can come back over here. This is the other nice thing about Kubernetes. You can hit L for logs, but since it's not started, there's nothing there. You can hit escape, and I can describe this container, and it tells me everything about it inside. And here we can see its image is coming from localhost on this port, and it's just the path to the container. So that's the Kraken caching layer. So that really speeds things up once they've been on the node once. It's really fast. And here we have all kinds of different my client ID information metadata, and we can see the persistent volume claims. There's my home volume. This is the MATLAB volume. This is the Xilinx volume. And I can see what it's doing, pulling the image. So it's the first time it's come into Suncave 9. Suncave is an interesting visualization system. It's I think it's still the world's largest high resolution cave. Here we got another one. David from Berkeley is coming on. So I can monitor these in real time. Oh, now we're both creating. And I don't think Suncave 23 had it on there yet either. So it'll take a couple minutes for those to spin up, but they will eventually get there. I was planning to have the entire Suncave cordoned off and preloaded with all the images so they'd only take 30 seconds, but I had to sleep last night apparently. So what else? Oh, I can show off the Docker file. This is the Docker file that we configured to customize this. By default, it's Ubuntu 20. So what I did is I just went to the Jupyter Docker stack on GitHub, and I found they had a Ubuntu 18.04 tag. So all I did was change the tag. And then I had to do a couple of minor things in the install script. Here's our KDE full. That was the secret sauce. And then a couple of other things that weren't included in this were LiveBoost and perf tools. The rest of this stuff is just kind of the things that I like to put in there for what I do. And then we grab Turbo VNC and do some permission fixing, make sure I can sudo to root without having a password, and then just git clone. And then added GNU Radio, and then we pushed the Jupyter Lab environment into reality, and we spawned this. And the YAML, oh, this is the license survey. That's not what I wanted. I come back to the other repo. So that was the proxy. Then the hub, this is how it gets spawned. It's basically, there's a Jupyter Lab hub Helm chart. And basically it's in our documentation. There's a how-to. If I come up to our docs, development, deploying Jupyter Hub. So we have a really easy guide if you want to spin up your own Jupyter Hub on Nautilus. You can just register your URL that you want to register it to, And a day later, they'll give you the authorization. And then basically you deploy this Helm chart with the customized template. And yeah, basically you just replace your URLs or whatever admin names and stuff like that, and spin it up. And then all of a sudden you have exactly what we have, but for your specific project. So in the last month, we've probably spun up 6 of these Jupyter hubs for different groups. This is the first one that's had Xilinx and MATLAB working inside it. So if we come back over here, let's see, one of these windows. It's making some progress there. Let's see. Okay, so yeah, both of those other instances are running, and we have one more. Mitch is firing one up.
And Wes is trying to fire one up. He said the CLI login is slowing him down a little bit. It seems to be taking a long time loading the identity for providers.
Interesting. You might just reload that page. Sometimes CLI logon gets a little busy.
Yeah, I'm trying it in multiple browsers.
Really?
Yeah, it's sitting there. It's taking its time.
Yeah, it recognizes that you're there. I can see you in the user list now, and apparently I can start a server for you. So it's sort of done something.
Yeah, I got in once, but then I closed my window and I'm trying to log in a second time.
Oh.
So, but yeah, I'll just wait
that it's trying to I know that if I've previously logged in, it just auto logs me in again if you've just closed the window. So it could be that it's just spinning for a while what it logs you in, because it sometimes takes that a while to happen for me.
So here's an example of the monitoring system that we've deployed. This is just Prometheus scraping the statistics about the Casper namespace. Are you guys able to see this okay?
Yeah, we can see it.
I wasn't sure if my network had popped off. So yeah, this it allows us to go back. Let's see what this looked like a couple of days ago. We also have Thanos, which gives us a decimated view of longer term archival data. So we can have a higher performance data set that is kind of spooled into a lower resolution. But we can come in here and click in here and get performance CPU load. He just spun up, so there's absolutely nothing in it yet. Let me go back to so the nice thing is you can monitor the performance of your application inside of this, no matter what it is. So we can watch IoT devices. Something is slow. Yeah, here we go. And let's see if I click on one that's been running a little longer. Okay. Here we go. Oh, and just moved. This will have some data. There we go. So that's the last hour. You can see the bandwidth, transmit, receive, also packet drops. And I was noticing earlier that some of the containers in the namespace were dropping packets. And so that's indicating there's one of the nodes is having difficulty talking to some of the other nodes. And when you do a globally distributed cluster, that's not uncommon. And so what we can do is we monitor the whole network using a tool called Reservoir Labs Gradient Graph, and it figures out choke points along the paths. And one of the things that we're going to be doing is deciding on pod placement. So we put the workflow in a place that doesn't have any choke points to the other endpoints that it needs to collaborate with in the workflow. Let's see, we're still creating on iGrok 02. By the way, you can see these right now, all the containers are spinning up in UCSD. This optiputer.net is all in UCSD. But some of the other nodes, like the proxy and this other, let's see, where was that? NicerNet here. The hub and the proxy, they're both running in New Jersey. And so it doesn't really matter where we place it. The only reason that we have to place them in San Diego is my network license server for MATLAB won't accept connections from other campuses. So we have to run them all. Oh, there we go. That last one just started. Cool. And so we should be able to come over to here and refresh this. Yes, a much larger list. And so I can drop into Mitch's. This is a nice little authentication warning that the admins get. And here's your Jupyter notebook. And I like to come in here. First thing I do is go to the dark theme because it's just too bright. And then the desktop. And there it is. It looks like MATLAB is starting, but minimized. Let's see.
Is there any way to hide the send Control-Alt-Delete button?
Oh, it's still waiting to finish, I see.
Yeah, GNU Radio started right up for me, but MATLAB is taking a lot longer.
Yeah, GNU Radio is small. It doesn't have 1 million files on the file system. It's got to go touch. There's also ephemeral storage that's available on pods. So you have access to the local NVMe that the operating system is running on. There's hardly anything used for the OS, so we allow that to be used for scratch space. And you can protect your containers by requesting RAM and CPUs, but you can also request ephemeral storage. So you say, hey guys, I need this, nobody else take it, and you don't have to use it, but you kind of reserve that on the file system. We do that for our Ceph storage nodes. Believe it or not, we allow user jobs to operate on our CPU-only Ceph storage nodes because we built them too big, too many cores, and we were just wasting CPUs. So we basically allow certain namespaces like the Open Science Grid. We know they're very well behaved CPU only jobs in these certain namespaces for Open Science Grid. So we allow those things to scrape up all the unused cores on the storage nodes. Anybody have questions? You guys interested in looking at
Is it possible to hide the Control-Alt-Delete button on the top bar?
Oh, yes, it is. That's just me editing the HTML, but actually I'll show you a trick. If I minimize this, I pop up a window, I right click, inspect, I select top bar, and I delete element, and it's gone. It's a hack until I fix it properly, but it doesn't.
Just seems too easy to click by mistake.
Yeah. Well, I don't think it does anything useful. So
okay.
Control-Alt-Delete, I think we can define in the desktop to do things. So anyhow, it might disconnect you, but it's not, all you got to do is reload the page and I think it'd still be there. So actually, one of the first things we did in a Jupyter lab notebook for somebody at Berkeley, I can't remember the name of, is we installed GNU Radio because he was teaching high school kids how to use it. I think it was for a SETI project. But yeah, it was a pretty cool, simple thing that we did for someone. Let's see. So how many people are familiar with the DevOps that are available in Jupyter Lab? The way it works here is basically I just cloned this repo from UVPanda. He's the guy that wrote this remote desktop at Berkeley. And I added this GitLab CI file, and it just pulls another container that is this Kaneko thing that does, it's not a Docker and Docker build, but it's just a generic chunk of boilerplate that we paste into any repo. And then over here in the CI/CD, we have these pipelines that get fired up. And so the last time we made an edit, this is the results of it. So we have the full log of it installing all the packages and going through. And if it fails, which it does quite often, you can look at the why it failed and fix it. And yes, it already existed because this was an older, this was a hack that I had done to make the Ubuntu 20 work, but that file already existed in Ubuntu 18.04. And so I had to remove that one line from the Docker file, and I hit save and it rebuilt it. And this one took 18 minutes to build. Let's see. Because it does it in layers, you can see if you build a base layer and then you change just some layer way down in the Docker file, it'll cache all those other layers. And so it doesn't have to rebuild them, it'll just pull it out of the cache, and then it'll continue from that spot. So that's if we go into the packages, the container registry, every repository has a Docker image registry and a cache. And so I can delete that cache, but it'd then have to rebuild the whole thing. So I can come in here and I can see all the tags that it's built through time. A little slow today. Could be my network. I am sharing, what is it, 7 desktops in one web browser. All right, so. Something went wrong. All right. It was a live demo. It had to break eventually. So, oh, the other nice thing you can do in the Jupyter desktop. Can you guys still hear me, by the way? I can never tell if my network is.
Yep, we're here.
All right, so I can fire up a couple of terminals, and I think I have a Python notebook here. Oh, this is not mine. I'm in the wrong. I'm in somebody else's notebook. Let me go. Where's mine? Here I am. And if I get rid of the desktop, I'm at my notebook. And so here, if I fire up MATLAB no display in a terminal, over here, And I can drag these around and make my desktop look nice. And it's going to fire it up. And when it does, I can run MATLAB in this MATLAB notebook. We'll see how it goes. And again, the file system is what's causing this to be slow. We will fix that. There's actually a pull request into the Ceph components that are being affected by this that should, well, we thought it got fixed in the release before last, but I think it might have crept back in because it was working for a while. Ah, here we go. All right, so I come over here. And hello from MATLAB. So I'm going to stuff an array and then see how long it takes to plot it. And also you'll notice that the MATLAB picked up the Xilinx shell. So we can do all kinds of fun stuff in the Jupyter Notebook in parallel to the desktop. So, and I can imagine for those new Xilinx modules, the $200 gadgets, this is going to be a really simple interface. We'll be able to proxy their Jupyter stuff right into this hub and be able to interact with their hardware in real time from a notebook. Other things I might demonstrate or talk about. You guys interested in the layer 2 networking stuff? The auto goal sense?
I mean, always.
Okay. So let's see. I think this is the right one. East. Or maybe not. No, that's not the right one. It's East. That's the one. So this is the Sense Orchestrator. This does require a login. It gives us a REST API. They have a Swagger document that describes their interface, and it allows me to turn on and off the layer 2 paths that ESNet has pre-built for us. So they don't want to give us control of the whole network. That would be a little insane considering my history. And so they give us predefined paths. All right, here we go. So again, CI log on our favorite thing on the planet. Oh, I've been forbidden. Awesome. Okay. Did I log in with the right identity? Yeah. All right. So they're updating things. Let me go to the public. I think this is the aggregator. Yeah. Okay. So this is kind of the YAML view, but this describes all the paths and the circuits that we have access to that we can plumb, basically. And so if we have an experiment where we have some site in Europe that wants to connect to some other site in California or Australia or New Zealand or wherever, we can ask ESNet to engineer the path for us. And anytime we need it, we can light it and then tear it down, like making a phone call. And so if we search for OptiPuter, we can see our aggregator here, and we can get into its metadata. And we can, yeah, it's much more fun when you have the user interface that works instead of staring at YAMLs. But this is all the things that we need to know about what port on what machine is connected to where. And so with these, yeah, here we go. So the aggregator and the NSI layers, and this is the switch. So you're when we light this up, you're actually programming VLANs to be plumbed on an Arista 7508. It's our backbone switch for our Prism Science DMZ. And so it's a considerable resource to give people the knobs to, but it's still a small group of people that have access to that for turning it on and off, and then only in well-defined environments.
I have a question about the upgrading of MATLAB versions that will eventually happen. Is there going to be some maintenance of the old versions as well?
I already have MATLAB running in the new, if we just go to our main Jupyter hub, I've got the, actually this is a good example. So here's our spawner page that we can extend to include FPGAs. So right now I can say, I can ask for up to 8 GPUs. The chances of me getting 8 are 0 today because of paper deadlines, but I can ask for 1 or 2. I can ask for 16 cores. I can ask for 16 gig. What flavor of GPU? So this is our garden of architectures. So we like to have a couple of everything. As a matter of fact, real soon we're going to be attaching a DGX from an NVIDIA DGX system that's at San Diego State onto the cluster. But we do have some other V100s and a lot of different. But if you want to be lucky and get one quickly, don't select one. We can also hook up shared memory for PyTorch, and this Ceph file system is going to bring in the MATLAB and Xilinx tools, because I had Dima, our admin, pull that. And so I'm going to grab a desktop with GUI. If we had FPGAs integrated into this, I could just ask for that and I hit start. And so again, it couldn't find anything right off the bat. And so now it's figuring out who's got a low priority queue that they can push out of the way. And that could take a couple minutes. But when it spins up, it's going to have the latest version of MATLAB and Vivado and Vitis. And we also, it's not in these toolkits, but we're also working on the early access release of the P4 compiler for Xilinx and Mellanox. We have both of their development environments. It looks like our container is found a host to live on and is spinning up. So this is the, this is the same type of interface that can be customized to include well, the other accelerators we have are Google Edge TPUs. The ASUS makes a 16 TPU, I think it runs like 70 watts for 50 or 60 teraops of performance. And it's a PCIe Gen 3 16 lane connector on a card with 16 of these TPUs. So we have one of those already in the cluster. We ordered a second one, but they're already back ordered. Apparently they're almost as hard to find as GPUs these days. But FPGAs, I mean, if you can afford them, they're there. You can buy them. We do have, for the networking side, we do have 4 machines with Bluefield 2. And they're connected at 200 gig to Mellanox SN3700 that runs Sonic Network OS. And another cool advancement in networking is the switch abstraction interface, which a whole bunch of vendors are buying into and using Sonic as the vehicle for this. So there's most of the major switch providers have bought into this. NVIDIA Mellanox have bought into it big time. They have, they got the data center on a chip, and Sonic is on their switches. And so we're using Sonic Kubernetes, which is a project in the Sonic work group that allows you to join the Sonic container. It's a Kubernetes container that joins your any cluster, and you can do K8s or K3s on that. And so that allows us to then orchestrate P4 containers to match the workflows of the P4 programming that you're doing on the SmartNICs. So the things that we're looking at are header injection at the container level. So you can tag your workflows at the namespace level. So all the bits and all the bytes are kind of labeled in metadata. And all this metadata can be mined through all the REST APIs that we dump it into. Prometheus, Grafana, Elasticstack, Ismond for the persona information, and lots of other things like Netbox for our start of truth, for the physical layout and the position in the rack. And so, yeah, we've also got some crazy things where we're mining our own data for visualization of our global wide area network. Actually, I think oh, I don't know my own password. That's better. All right, so here we're in a Windows box, and this is Unreal Engine, and this is Atkinson Hall. Let me just hit play here. And so we have a photorealistic rendering of our building and data centers, and in this, oops, whoa, I don't know, I must be Superman today. Yeah, something's going crazy here. Well, it looks like it's going to be impossible to demonstrate, but in this model, we have every Ethernet jack in the building wired. There we go. There's a cable tray. So we know where all the conduit, all the cable tray, all the fiber runs are. And Netbox stores all the information about where they're physically racked and what slot in the rack. And so our goal is to have Unreal Engine call the REST API from Netbox and render our entire building's cyber infrastructure with live metadata. And unfortunately, this is moving way too fast to navigate properly.
Oh, we are living in a simulation then.
What's that?
We are living in a simulation.
Yes, absolutely. Yeah, sorry about that. That was overloading my laptop. One too many screens.
I have a more basic question. So we use this, MATLAB system generator interface and everything, and we've put our design in there, and we hit compile, and we get a bit stream at the end. How do we get that into our lab so we can put it onto our FPGAs?
So
download file.
You could attach the FPGA, even some of the developer kits to these things using another, they're called device manager plugins. So we use one called Simpler Device Manager. And the reason I like it is it does IoT. So you can kind of put K3s on your Jetson Nano, and Kubernetes can provision the GPIO ports, the I2C ports, the GPU. It's just like a regular machine, and you can slice it up and use parts of it. So we can talk to like USB or serial JTAGs. So you can have a sidecar container that has the JTAG, and you can upload or do whatever you need through that. We can mount virtual storage if we have to through, we have these $200 Raspberry Pi lights out manager gadgets that we're putting on things that don't have lights out managers. Of course, then they don't have a lights out manager. So what we do is we gang all those IoT lights out managers to a remote power switch, so it can power cycle all of them at the same time. But it does give us a backdoor into some of these Jetson Nano and Google Edge TPU gadgets. We have 32 of the Google Edge TPUs that are not currently in the cluster, but in development for being installed in physical spaces like our data center. So if you want to interact with the room is watching you. So it can understand what rack you're pointing at, and pull up in your HoloLens a console for that. So our goal is to have a full AR immersive network visualization tool that scales from global views all the way down to the exploded view of the server, showing you which card to pull out because it's overheating. And we have all that metadata, as a matter of fact. We collect IPMI of the fan speeds of every single GPU server, actually every server. And so in our Unreal visualization, we have a team of students, 3 of them are working on spatialized audio that will recreate the cacophony of the fan noise of the data center, just because we can. Don't want people to miss out with that. But we can also use that same cacophony to bring awareness to problems. So like GPU-03 server has got all of its fans locked to 16,000 RPM, and it's it's going to wear them out in a minute because it's in a coma. And so we need to go and cycle and do an IPMI power reset on that guy to get it out of its coma. And so we're going to be doing a lot of machine learning. We already have a whole bunch of machine learning bots that scrape our logs and alert us in our chat rooms when things are locking up. And as a matter of fact, if we see somebody spawned a job on a GPU node and it's totally borked it, one of the GPUs, the only way to get those unlocked is to power cycle, or they won't reattach to the PCIe bus after they've overheated. So we wait for the priority jobs to finish, but we cordon the node and queue it as soon as that job that can't be interrupted finishes. It reboots the node and those GPUs come back. So we're doing a lot of automation that you guys might be able to take advantage of. And it's all doing using Ansible and Netbox, and the whole stack is fully open source, except for the Xilinx and MATLAB stuff that we just put in there for fun. The framework to run all that is free, though. You can add any app. We've actually containerized Houdini, Unreal, Blender, all the high-end 3D authoring tools, what's that, Paraview, multi-screen simulation engine. That's really cool. We have a 37 node, 70 screen, the Sun Cave. Basically, we can run containerized visual apps like ParaView from the cluster in that system using MPI. So a full MPI enabled visualization cluster that when it's not doing that, it's doing TensorFlow for some guy's Jupyter notebook.
My screensaver kicked in on my desktop and I don't know the password to unlock it.
Yes, that is one of those issues. So what you do is you go back to the notebook side where you pop up a terminal and you have sudo with no password. And so you can sudo set the password to the Jovian user to whatever you want. Yeah, we'll figure out ways of tweaking this installation to not have the screensaver come on after 5 minutes, things like that. And any other tools that you guys need installed, just let us know. We just push them into the Docker file and 10 minutes later, it's done. Questions?
So our design did finally finish compiling.
Oh, let me
point out. But other than that, I did fix the mlibdevel bug, hopefully before everybody downloaded it, like a couple of hours ago, so, or an hour ago. So most repos should be good.
So there it is. So compared to normal, how long did that run? Was that
one took a really long time. Yeah. That took about 6 or 7 times longer than normal. But when I ran the full tutorial compile yesterday, that took a very short amount of time. That was sort of, I'd expect that to take, it was under an hour, and I would have expected it to take more.
So the difference is you're running on the early version. This is a PRP v0. It's a pretty low performance system.
Yeah, whereas yesterday you had me on some powerful thing.
Yeah, anything that's got iGrok or Gen 4, those are all brand new 100 gig connected monster machines. So yeah, you get what you pay for, or whatever you look out to. But yeah, we can target individual nodes. Yes, we have some nodes that have 196 cores. So if you needed a lot of CPU cores, we could spawn it there and just suck them all up. You have to leave a couple around for the hard drives, but you get the idea.
Yeah.
And that's where did the desktop go? Here we go.
Otherwise, we're running past time, so I guess if there aren't more questions, maybe we should wrap up.
Sounds good. Very cool, John.
Yeah. Well, I'm glad I can help you guys.
Yeah, well, I'm just happy to see it running after we've been talking about it for a good couple of years. It's really nice to see it happening.
Well, like I said, anything that you guys want for customization, Berkeley is 1/3 partner in the Pacific Research Platform. So anything you ask for, we do. So ask away.
And that's you may get in a lot of trouble with that offer. We really appreciate it. But I've already started because this project's going so well. I've got a couple others with SETI Home and Pano SETI that I want to talk to you about.
Yeah, it would be trivial to spin up another clone of what we did with customized tools for them.
Thanks a lot, John. Great stuff. Take care, everybody.
Yeah,
Bye-bye.
thanks everyone, and we'll see you all again tomorrow.
Thanks all.
Thanks, John.
Sounds great.
Thanks, everyone.
See you. Cheers.